Welcome everyone. Welcome everyone to day 3 of Understanding Latency 2.0. My name is Björn Ivar Teigen, and I'm head of research at Domus, and will be your host this morning, afternoon, or evening. So first, some practical details. We have a series of 15-minute talks today as well. And after each talk, there will be a Q&A if there is time. And to ask questions, please use the Q&A tool that's built into Zoom. That makes it easy for the panelists to see all the questions and make sure that we don't miss any questions. Also, feel free to use the chat. You can try asking questions there as well. Might work. And do note that the whole session is being recorded. We'll put it up on YouTube after this, and your questions, the chat and stuff will also be part of those recordings. So don't say anything you'll regret. Finally, I want to shout out that we had great sessions Monday and Tuesday as well, and they will be made available if so. Everyone who signed up will receive an email with links to the recordings and the PDFs of the slides for all of the sessions. That is it for the sort of technical or the practical details. So please let me introduce today's first presenter, Dave Tott. He'll be presenting a grumpy look at the state of network latency. Was his preferred title today. He's been part of the Bufferbloat project for a long time. He's a co-author of FQCoddle and Cake, and for the last, I think, year or two, he's been the chief science officer at LibreQOS, who's doing very interesting stuff in the ISP space. So please, Dave, take it away. I can see your slides. They're loading. You're still muted, so I can't hear you at the moment. Seems you're muted within the Zoom tool. There we go.
It helps to be awake.
Now I can hear you.
Am I awake now? Can I be heard?
You can,
Great.
yes.
All right, going back to my slides. Am I still with you?
Yes.
I'm still here, guys.
Yes,
Great.
you are. We can hear you, see you, and see your slides.
Great. So anyway, I am Dave Tott. I have been doing the Bufferbloat project for almost 14 years now. In the last couple years, I went and focused on making life look better at the ISP. And I wanted to talk that I'm less grumpy than I've ever been. Guys, congratulations. Pat yourselves on the back. We have come a really long way in the understanding of this problem, and all the tools that we have become really great. And I've given a lot of other talks that are a lot more fun than this one is. This is a very short talk about some of the things we've been doing with LibreQOS to make things better at the ISP. As noted, I'm one of the authors of Cake and FQCoddle. There are dozens of other people that have been involved, and I always want to give them credit. John Morton is, for example, the principal author of Cake. FQCoddle for Wi-Fi was done by principal authors Toki, coming up after this, and FQCoddle itself was designed by Eric Dumazet with a wonderful, wonderful influx of Kathy Nichols' call and algorithm. So because it was developed almost 10 years ago, it's now a commodity. It's almost ubiquitous in all the gear in the WISP market. You can just turn it on MikroTik. You can turn it on, it's on by default on things like the Eero and so on. It's just there. It's also the default in Linux, and it's everywhere. And to be a little grumpy, you don't have to change the whole internet to be using it. You just add the flow queuing, the multiplex everything back together better, and the AQM to keep the queues short. Most flows are pretty low rate and they automatically experience zero delay. It's easy. Um, I am a huge proponent of flow queuing, particularly because it does protections against misbehaves and greedy flows, and it completely mitigates the side effects of slow start. So it's a big internet, guys. Bandwidths are universally going up, but along the edges, we still see 5 megabits, 10 megabits. And this is the places where trying to also manage the latency better is really the most important today across the entire global south and along the edges of the internet. And despite all the people going for cloud computing, this and that, the other thing, we see 30 megabits per second at peak for most of the subscribers we're seeing using Libre QoS. I skipped ahead. So I'm a huge proponent of cake as well. I keep trying to get people to duplicate this particular slide. This is the effective latency of the TCP cubic algorithm with a FIFO, seeing good put degrade over time with a 250 millisecond FIFO. And then there's BBR, which does marvelously better. And then there's cake versus cubic, which does even more marvelously better than that with nearly perfect throughput and about 10 milliseconds additional latency. So Libre QoS is open source software. It's free software. Anybody out there, small ISP or interest in this, can download it, turn it on. We've managed to take the cake algorithm, which we first prototyped on a 400 megahertz MIPS processor, and scale it up to a Xeon. And it can push 10 gigabits through one cake instance, or we can push 10,000 subscribers through 10,000 cake instances, which is 4 million queues, by the way, and only eat about 50% of CPU on a given box. So any ISP today can go to eBay, get a reasonably, not even a modern box, and be able to manage a rather large segment of their network with a single box for it. Got it to where it's simple now. It takes about an hour to set up, and you have to integrate it with a few other tools, and boom, it works. Now, this is the very first time in 14 years that I've actually had a business model in that the core engine is free, but we have a statistical model that takes a look at long-term stats across the entire network, which is actually for pay. So my hope is that that will help drive further development onto other things later on. So long-term stats, basically we decided on color coding things. 35 milliseconds is an outside number for almost anything. And then as you get worse and worse, those are the kind of color gradations that we have to try to show an operator what is good and what is bad. Simple, no numbers. So throughout this entire conference, okay, I'm curious, are you guys seeing this stuff here? I just flipped back off of this thing here. Am I here, guys?
We see the slide that says, but what is network quality anyway?
Okay, great. Thank you. And it's kind of this indefinable thing, it's the absence of pain. It is the presence of flow. It is and when you click on something, something almost immediately happens. It's uh, your spell check comes up immediately with the right thing. It's the absence of something rather than the presence of something. And when I started researching this talk, I was on a train ride and I asked dozens of people if they know how the internet works, and the answer, and none of them was zero. 0% of people even understood what a packet was. And I realized that, we have a long way to go to education. And at the same time, we don't need to necessarily educate. We just have to provide the absence of pain in using the internet. So we're working on this. We have a ton of tools. In fact, let me put one into the chat. It was hard to get the animations into this particular presentation. So I'm going to plunk into the chat. One of the many users of LibreQOS went and started taking movies of what different kinds of traffic actually look like. And I'm going to show off a couple of those, but if you want to watch some of those, it can be quite mesmerizing as to what Netflix looks like and what real traffic actually looks like. We see a lot of aggregate measurements for here and there, but deeply understanding what just one kind of traffic looks like will hopefully lead to more intuition in the future for more people. Thank you. So back to that. So this is one of the many plots that you can get, live plot on a 10 millisecond interval you can get out of traffic going to a given customer. In this particular case, we are pulling out diff-serve information. So there's a couple packets that were marked bulk. We have a bunch that are marked video and a bunch that are marked voice and a bunch that are marked regular stuff. And any amount of dots here means that you had some queuing delay. But you can see how low the queuing delay was for the specifically marked traffic, and it's pretty low for the other ones. Most flows are really short. Another tool in LibreQOS we put in is a thing that plot mice and elephants plots from the famous 2002 paper about mice and elephants. And it's just remarkable how few flows are actually elephants. Still, if you're an operator and you're sitting there wondering what's going right or wrong on a given connection, it helps to have these wonderful graphs of how the overall connection is performing for that particular user at that particular moment in time. So we gather these sorts of data on behalf of each customer of an ISP, and they're able to very quickly, the operator very, very quickly see if there's something that's gone wrong with the link. And you can also see the total amount of traffic and a live amount of what the TCP round trip times are. We get a little flack for this. Rather than show customer names, we translated everything in the Klingon. It's a geek joke. I like it. Other people don't. One of the really big things that I keep harping on is that slow start is a big problem. It is possibly the biggest problem we have in terms of the overall amount of loss and amount of jitter that gets inflicted on the internet. Netflix in particular looks like this. A couple bursts of slow start and then a pause. A couple bursts of slow start and then a pause. And without flow queuing, those are very apparent to the end user, and there's not a lot you can do about it. With flow queuing, it becomes completely invisible. Here's another plot. Again, I put a link into the slides here of what Amazon Prime looks like. And you'll see that in this particular case, this guy is going at good, almost 30 megabits, pretty solid. The Q links are all over the place. And it doesn't really matter because it's all masked by flow queuing. So we have some more detailed plots involving looking at throughput and TCP latency and through round trip time. But when you're an operator, the thing that you care about is looking at your whole bloody network, every single possible tower. In this case, this is just one of the largest sites. Everything's blurred out for you. But when an operator can look at their entire network and see almost everything in the green like that, that's a good day. Because there's always something that's breaking. Always cut fiber, or a DDoS attack, a squirrel here, a squirrel there, Wi-Fi problems. We're leveraging the wonderful passive ping tool developed by Kathy Nichols to be able to give us this unbelievable level of deep insight into the performance of the entire network all the way to the customer Wi-Fi. And that's really about it, guys. We have about 200 operators in the chat room, all contributing. I've learned an awful lot about how ISPs work and how although it's very important to be controlling and managing latency, just how many other difficult problems that they face in order to be able to deliver a wonderfully consistent, reliable, happy making experience for the customer. So thank you very much for having me today.
Thank you very
And
much,
I'll take
Dave.
questions.
We do have a couple of questions here. So Jason Livingood is asking, large ISPs get a lot of heat when they deploy traffic shaping middle boxes in their networks. What do you think the regulatory implications of those middle boxes may be in the future in the US with Title II regulations? Would there be more pressure to eliminate those middle boxes, or would they be impermissible? You have any
Yeah,
thoughts on that?
I don't know, Jason. I'm hoping that with a sufficient amount of education, showing, demonstrating the benefits, that we would actually see the value. We were say, well, why didn't you do that before? That's really been my hope. In the link there, we just did a big posting for the FCC explaining the benefits of this kind of stuff. There are certainly cases where middle boxes were bad. The DPI thing that happened with BitTorrent, that was dumb. But here, all we're doing is we're managing latency better. And I would hope they would embrace it. Next.
All right. Thank you.
CPU usage. Oh, okay. So another one from Jason.
Yeah, we just need to read the question out loud because the audience does not see the Q&A box that you
Okay.
see.
In the chart, so the CPU usage is part of the LibreQS monitoring system. Yes, and the RAM usage as well. We're using it uses very little RAM. This entire system is written in Rust by Herbert Wolverson and by Robert Chacon. It uses trivial amounts of memory. We could actually run the whole thing out of cache. We could shrink the thing down from currently hosted on a Ubuntu system, and we could probably get it to run in a couple hundred megabytes. But right now, we're requiring about 16 gigabytes for 10,000 users. We can put trying to clarify in our model, we can model the entire network to 8 layers deep, and the shaper box should be going fairly close to the end node on it. So the closer to the customer you can get the box, you can put as many as you want in. So hopefully from the reasonable explanation. Do I think L4S might help or hurt KKQM efforts? So I like multiple parts of L4S. I'm have support pending for some of L4S and Cake itself. I think highly of the NQB concept and of some level of DipServe for certain kinds of traffic. So I'm looking forward to that. And I'm following all the tests and we will track them. One of the nice things about the fact we're doing this in a middle box is that I have an ISP's perspective as to what works and what doesn't, which I never did before. And B, we can really observe what the packet loss rates and rates really are for real traffic. And I've seen a lot of numbers go by in this conference for what the loss rates are. I don't see 1%. Once you crack a 50 megabit download, 1%, you don't see those kind of loss rates anymore. So it's a brave new world. And I'm hoping that working up from the bottom and improving Cake incrementally to also support some L4S features will be great. And I hope that L4S also supports some Cake features in the future.
Cool. Your voice is or your audio is breaking up a little bit, but I hope everyone got what you were saying there. I think I did. Let us know if in the chat if something was unclear.
I'm sorry for not getting this. Yeah, I'll answer more questions in the chat. I'm sorry I'm in Morro Bay today. I can show you some pictures of some sailboats. So thank you for having a wonderful conference so far, everybody. It's been really great seeing all.
Thank you so much, Dave. Appreciate the talk. All right. So I think we'll move to the next speaker now, who is Toke Høiland Jørgensen, and he'll be talking about always on latency monitoring with eBPF. So Toke, please take the stage.
Yes. Hello.
Hello. We
Can you hear
see
me?
you. I can hear you well.
All right. Let's see if.
Oh, hi, Toki. Great to see you.
Hey, Dave. All right.
Now
Did
I
that.
can see your slides as well, Toke.
Okay. Cool. I can't see them myself, but I guess that's all right. Okay, so I will be talking a little bit about what we can do with eBPF. There's a little bit of overlap maybe with what Dave was talking about, because the LibreQOS system has some shared geniality with the tool I'm talking about today. But at the last of these seminars, I talked a little bit more in general terms about eBPF and what it does and how it can be used to improve latency in systems. And since then, we've had some more development on one of the tools that I was talking about at that time. So I'm going to go into a little bit more detail about this and show some examples of what we can do with this technology, and also in a sort of Linux middlebox context, I guess. But first, to preface this with that this is joint work with Simon, who's a PhD student at Cal State University, and his advisors, and some colleagues of mine, and Robert from the WISP that I will be showing this from. But for those of you who don't know, eBPF is this technology that we've had in the Linux kernel for quite a while now. I think it's almost a decade. But it's sort of this instruction set where you can inject some bytecode into the kernel. It will be JITed into native instructions and injected into various event-based hooks all over the kernel, and it allows you to access kernel functionality. And then it's sandboxed, so it sort of prevents you from doing a lot of the stuff that you would be able to do with a kernel module, like, for example, crashing the kernel if you made a mistake. So this sort of opens the floodgates for this functionality that we can inject into the Linux kernel. And one of the first uses of this, and also one of the big uses still, is, of course, networking, where there are various hooks around the kernel where you can inject the BPF code, and it will be run on every packet that comes through the system. And so if you do this, if you take this technology and you combine it with Kathy Mitchell's p-ping utility, the passive ping utility, which is basically the idea we started out with here, you get the EP-ping, which I forget if we decided that the E was evolved or enhanced or something. But if you look at this graph, basically what you see compared to the baseline, the blue line is the baseline, as which is the forwarding rate on a single CPU. Like you pin the traffic to a single CPU, and this gives you these almost 2 million packets per second of forwarding capacity on this particular machine. So like the absolute numbers are not so important here. The important bit is sort of the delta down to the green line, which is the EP ping, and then the bottom orange line is the user space p-ping utility, how many packets it can actually process. You see it falls off a cliff because it's like it's not the fault of Kathy's utility so much as it relies on libpcap, so it copies all packets out to the to user space, which doesn't scale so well. So basically, this is a straightforward sort of porting of the utility, which is what we started out with. There's a reference to the paper there that describes this version of the utility. So what this allows us to do is that we can run this with acceptable overhead on a Linux forwarding middle box and look at every packet and process every packet while doing this latency measurement. And what does this look like? So this is just running the utility the way you would normally do it while refreshing the understanding latency web page, which lives in the 198.49 IP address you see there. So it will start sniffing traffic, and you will get a few RTT samples, in this case, 21 point odd milliseconds from my machine to that machine. That's pretty cool. It's just looking at the timestamps on the TCP packets and gives you the RTT of the actual TCP traffic as it's going back and forth. However, if you do this at 10 or 100 gigabits, you will get a lot of output, and that doesn't really scale to the kind of continuous always-on measurement that we were after here. So, so what we did was we added an aggregation mode that we can, with which we can enable always-on monitoring. So in this case, the -- aggregate argument to the utility gives you an output every 10 seconds, and I just included one of them. There's a lot of output you can see here for each /24. For IPv4 traffic by default, you will get a number of packets transferred in both directions, how many RTT samples it managed to collect, and then some statistics over the RTT while this was going on. And you can see the minimum RTT was the same 21 milliseconds that the samples we saw before for this subnet. And then it goes up to almost 30 milliseconds in this case with those samples. So this is just to give you an idea of the output and what kind of data we're collecting. This is again not sort of the most useful format. This is the interactive mode, just to show how the tool works. But the interesting bit comes then with the JSON output mode, which will give you not only these samples and statistics, but will give you the whole histogram for each subnet that you have configured. You configure the subnet size, and it gives you the whole histogram and all the statistics for each subnet. And we ran this for a month at a your friendly neighborhood WISP on a LibreQoS box that Dave was just talking about. And the paper for this is under submission, so I'll just show you some different graphs from it to give you an idea of the kind of things that you can extract from this, and some interesting things we saw while looking at this data. And my hope is more that you will take this and use it as an inspiration for running something like this on your own network and drilling into this some more. I would also be very interested to hear any ideas or features or particular types of information that people are looking for in this that we can work with in the future. So one thing you can do is you can create these heat maps of the entire IPv4 space. So this is this, some of you may be familiar with the HKCD map of the internet, which sort of uses a Hilbert curve to snake its way through the subnet size. So the top left one, you can see there's a faint blue line, which is the numbering of the subnet. So each number is just like 0 is 0.0.0.0/24 and so on. But this gives you a heat map of from the measurement point, which is like in the ISP backbone, and out to each of these on the WAN side of the link, the RTT distribution for that subnet aggregated over this whole month. So it's a lot of data that sort of gives you an idea. And of course, a lot of this being different parts of the internet, a lot of this is based on geographical distance. I believe there's a cluster, like the big red cluster on the top right in the middle is either Europe or Africa. This was a measurement taken in the US. So there's obviously a geographical component to this, but you can also see, comparing the min, median, and P99, you can also see that some subnets have a lot more variance. Also, of course, the standard deviation on the bottom right. So this can give you an idea of your, if you're an ISP, it can give you an idea of your connection quality to these things, or it can show you any peering link problems or things like that. We also aggregate like the amount of traffic that goes to each of one of these, so you can also use it as a just as a way of monitoring the traffic on the network in general. Another thing that we looked at that we are collecting here is the different protocols. So most of the traffic is obviously TCP, but we do have a sizable fraction of UDP traffic. This is the fraction of packets, so not necessarily in bytes as well. But we do see 27% UDP traffic in this case. We also, being nudged by Dave to do so, actually, we started looking at how much ECN usage is there in this case, and the answer turns out to be almost none. 80% of the 98% of the traffic that we saw had no ECN marks. None was marked as not ECT. We did not, in this case, gather the echo back. This is just the IP header markings. But given the fractions here, maybe that's not too important here. And then, of course, the last one is the frequency of timestamps, which is important because that's what we use to gather the RTTs. We also gather, so as you can see, this goes up to, for certain subnets, 40-something% has timestamps enabled. And the reason for this is that Windows doesn't enable timestamps by default. So this is only available for Linux and Apple-based clients. And without knowing exactly on this graph, my guess would be that the big spike at the side there would be Android devices connecting back to the Google mothership. But this is also just a sort of a way you can get aggregate features to show some of the statistics that you can gather with this kind of inline granular traffic collection facility. And then, of course, you can look at just the LAN side and the WAN side of the measurement point in this case. And what we tried to do here was to see if we could see any correlations between traffic volume, which is the black line is the throughput, like the solid black line is downlink throughput, and latency, which is often an indicator of buffer load. And if you look at these graphs, you can see that on the WAN side, there's not so much of a correlation here, but on the LAN side, there's a lot more stuff going on. And our hypothesis here is that it's actually the Wi-Fi links of the customers themselves that are suffering from buffer bloat and latency variation, and not so much the internet link. So that's sort of an interesting feature that we saw from this. And drilling down in this way, of course, is also useful if you want to debug your network. So that's sort of a quick overview of what you can do with this kind of technology. So we can passively measure RTTs at scale on any Linux machine. So this can be deployed to servers as well if you're running a server cluster in the cloud, you can put this on the host side of your Kubernetes cluster, for example, and get this for all traffic leaving the box. Or you could put it on a middle box, as we did in this case, and you can get RTT measurements and a lot of other measurements at scale. We can aggregate this per subnet, and we can do this efficiently enough that we collect it over the whole internet. And then you can use it to look at various characteristics on the WAN and the LAN side. So the idea here is to give you an idea of the capabilities, and with the hope that you will deploy this on your own network. We are also personally, my interest in this is also to getting this to a polished enough state that you can deploy it on your home router and keep track of your network in real time, also at home, or in these small middle boxes, which we have a lot of Linux-based machines that does this. So there's still some work to do. And as I said, if someone has any ideas or questions for things that we can add or specific features that would be useful to look at, we are also very receptive to adding these features. And the tool is available on GitHub. It should run on reasonably reasonably recent Linux distributions. You just compile it and you run it, and it either outputs the interactive statistics, as I showed in the example earlier, or it can show you the aggregated output either as JSON or human readable things. And like, of course, once the paper is published, we will also be sharing the data set and the tools we use to analyze it. But that will be a little while yet. And I can see I spent way too little time of this. I could have included more interesting graphs.
Yes, you could. We are ahead of schedule, but that's not a big problem. So thank you very much, Tuka. We do have a couple of questions. So Robert McMahon is asking, do you have data on DSCP QS markings? And if so, like how much is that used?
No, I don't believe that we gather those. It would be like we already look at the IP packet headers, obviously, for the ECN, but I don't think we gather DSP. So one question here is, are you most interested in like how much is it used, or would it be useful to store every code point?
I don't know, Bob. What do you think? He's saying how much. He's saying how much is it used?
Okay, so mostly a sort of is it set at all?
Yeah.
Yep, that's a good point. Noted.
And another question, also from Bob here, is do the eBPF RTT measurements match the TCP info stats on the end hosts?
Yes, I believe so. In the first publication we did on EPPing, we did some work on verifying the accuracy of the timestamps, and I don't recall off the top of my head if we specifically compared it against the TCP info. I think we might have. We also compared it against ICMP ping. Like EP ping can also pass ICMP packets, so you can also extract timestamps from pings. I don't think it's on by default, but we did some work on that. So I would refer you to that paper for the verification of how accurate these are. There's a couple of, like, the fact that it's using timestamps to get the latency measurements means that there are a couple of sources of potential inaccuracy in the latency measurements because of things like delayed ACKs and ACK compression and so on. And that's like we've also one of the things we've discussed is also adding the capability to get this from, to get the timestamps, also to do like set sequence number analysis and just collect it from that. But that gives a different side of trade-offs. So for now, we're keeping it with the timestamps, but for example, that will also allow you to extract RTTs from TCP traffic that doesn't have timestamps, like Windows. And also things like supporting quick could also be really interesting, to the extent that the spin big is
Yeah, I
used
saw a
for this sort of
question in
thing.
the chat about that. People are curious about how much of that UDP traffic is actually quick.
Yeah, I don't know, but
Right.
my guess would be most of it, like that, apart from DNS.
Yeah.
But yeah, no idea.
All right. Final question is L4S CE marking rate via eBPF capture would be interesting too. I guess that's not a question really.
Yeah, but we are capturing all 4 ECN code points. So you should, like, for alphas, you don't really know what it means, right? You just know that it's there. But if I go back to this graph, you do notice that there's like both EC and ECT0 and ECT1 are there.
Yeah.
But obviously, this determining what those mean, if it's an L4S sender that sets it, or if it's just an old style ECN that just uses them interchangeably, is like fundamentally not something you can extract from the data packets, I guess.
Right. True. All right. Thank you very much. And if people have more questions, you can use the chat to ask. All right. We will move to our next speaker, who is Neil Davies, who is the Chief Scientist at Predictable Network Solutions, or PNSOL, and the inventor of the quality attenuation network metric, and a contributor to various open standards and many other things. I hope Neil is ready, because we are 5 minutes ahead of schedule. So, there you are. Excellent.
Neil is not actually ready. Neil was far too fascinated in listening to what everybody else did to realize he was next. So there will be a short delay while I just get the presentation up, if I may.
All right. Very well.
And then I will join you. And here we go. Zoom.
We can hear you well, so that's good.
That's excellent. I mean, you know, on a call like this, you really want to be able to, you know, deliver the quality, guys. Otherwise, what would we
Indeed.
do? Yeah. Okay. I am going to put this into view mode. Full page. Wait a minute. Single page, and then put it full screen. Does
Yes,
that work?
that's working well. We can now
Right,
see
yeah.
the full screen presentation.
Just as you're not okay, I was going to go in rattles with this because I thought we'd be late, but Dave, I mean, I can tell you, Dave was reaching for this issue of the, you know, the absence of something and all the rest of it. I mean, one of the realizations we came to many years ago was that actually the thing about quality, the thing that what we want is actually it's about a privation, right? And a privation is the absence of something. So what it is, we want the absence of this stuff that I'm about to talk about, right? And you know, it's like the absence of noise in a room, or the absence of noise, or the absence of dark being the absence of light. One of the big problems we've often find talking to this about people is people want a box of it. They want a box they can put in to make the problem disappear. Like they want a box of dark or a box of silence. And I think, you know, one of the things that, you know, I think we all know is that actually it's not that. You've got to stop the light and the noise being made in the first case, right? So what we really talking about, what is the really thing behind the latency, right? And the thing I want to talk about here is this quality attenuation, that very thing that Dave was grasping for. There is actually a whole mathematical concept of it and how to capture, manage, and manipulate it, right? And what I'm going to try and cover here is these four points. You know, understanding latency isn't enough for solving the problems that we have. How do you capture the requirements you need? what do we need for real understanding, and what can we do to make things fun, right? And I think some of the questions about how do we sell things to regulators and all the rest of it, I'll touch upon as we go along. Right. Now, this is the real key thing. If I don't get anything else over to anybody, you can't think about delay and loss separately. You have to think of them together. It turns out that the whole thing is a system with 2 degrees of freedom. And for people with a mechanical engineering degree, they can now leave because they've got everything they need to know. For the rest of you, 2 degrees of freedom, if that doesn't sort of make your hair stand up on the back of your head, then I'm afraid you need to learn that that's one of those fundamental things that in basically system design you need to know about. Right? You've only got 2 knobs in this game. You hesitate a third. You can't use it with one. You have exactly 2 things that you have to control. Right? And why are we dealing with what? Because actually the delay and loss together are the things that affect application outcomes. And this is not just a concept, right? You will find, I'm sure if you watched Gavin's talk, he will have talked about this. And I've stolen a couple of slides from Gavin Young from Vodafone. But it is basically a nice concept that permits you to capture a whole bunch of properties of elements in the chain, not just network elements that handle packets, but also computational elements. We have designed protocols and distributed systems using this technique that deliver information on a global basis to tens of thousands of nodes sub-second, 24/7 for the last 7 years. So this stuff is real value in that sense. Okay, so delay and loss is the constraint here, right? If you want a TCP throughput of X, then the constraints that you have is you have a constraint on the round trip time and a constraint on the loss rate. This is just a graph from the standard mathematical equations for this property. To the left of this, on the left-hand side of this graph, you start hitting congestion window size, maximum congestion window size issues. And to the right of this graph, you start hitting the fact that you can't get the TCP stream started properly because the loss rate's too high and you can't get the window open enough, okay? But in the middle, this holds. So, for people designing systems who want to say ship, I don't know, 25 megabits per second, if your loss rate's greater than 0.2%, and I know, I have seen this on production networks in many countries where it is, right? Then basically you've got to be within 10 milliseconds, or you can't actually achieve. So the key thing, the thing I'm trying to get across here is that this is basically, you have to think about the loss and delay together, okay? Let's see if there's any questions. No questions at the moment, okay. It's a well-founded approach, mathematical, right? And basically, it allows you to differentiate between what's in the supply chain and what's coming up because of congestion and contention, okay? And you could even talk about the congestion that a customer, or the effects that a customer causes to themselves, or the effects of sharing resources with customers. This stuff we've covered before. I'm just bringing it up for those who haven't seen it before. But this issue is you can actually split the problem of this loss and delay into stuff that happens because of geography, right? Stuff that happens because of serialization and deserialization delay, and stuff that happens for queuing, buffering, and other things, right? And it's not just the bandwidth, you need the quality. Without the quality, you haven't got an application outcome that you want. So what's the significance here, right? Part of the reason why we have all this delay and all this loss is actually we have to have it because, or we have all this buffer bloat because in some respects we have to have it in order to have an economic internet, right? We have to do all this sharing, and the consequence of this sharing is that you are basically going to get variability, okay? If nobody else was on the Wi-Fi channel and there was no other person speaking, you get a very good service. So it's not about, it's about the sharing that causes this issue. But actually, you also need to be able to pull out from the problem those things you really can't change. I can't move Europe closer to America except over geological timescales, and I think they're actually going apart at the moment, if I'm right, if correct, right? You can, the underlying properties of your last mile technology can have a non-trivial or dominant effect in some cases on what you can do with your systems. Hopefully this is just making sense, right? This is right now. But the really nice property of it is you can decompose it. So you can actually, once you've got your head around this fact that you're interested in the loss and the delay, you basically start to be able to talk about where the budget is going for the loss and delay, how much noise people are introducing, some of which is sort of a noise floor, and some of which is a floor, an addition because of the interaction of queuing and scheduling. And you can start to talk about the end-to-end digital supply chain. Now, you can start for the ISPs that are trying to fix their own internet, they will find that they can't do much beyond their boundaries, right? And if we're going to use all of this stuff for a long-term civilization, we've got to start thinking of how we can actually deliver end-to-end with assurance. Okay, that's sort of the aim here, is to make a good end-to-end service that delivers. Okay. Because it's arithmetic, because it's maths, it isn't just about measuring. It actually supports issues like design and in-life management. And there are even people in universities doing it entirely mathematically to build these tools in which you can actually pre-design the performance of your system and check that it will work before you've even written a line of code or bought a single box. So, this stuff is taking off not just from a measurement perspective, but from a performance engineering perspective. Okay, and because of this, you can relate quality of experience things to the delivered the quality of service, the delta Q you get, and you can say, given that I have a particular, if delivers, given that you do given this delta Q, it will deliver this type of outcome, right? And it will deliver this outcome if it has this type of delta Q that you give to it. That duality means you can start to embrace the notion of delivering assurance and services, right? Agreed. There's a whole issue of what does it mean and how, the framework in which you would market, sell, manage, contract that issue. But the nice thing about this delta Q stuff is it basically acts as a universal proxy. So, if you measure this stuff, and you can do it, by the way, continuously, it's basically a 16 kilobit stream if you want to play with it. It works. If you look at the Broadband Forum's work on this area, you can support continuous monitoring of paths at a low cost, and because of the mathematical aspects of it, you can do statistically sound aggregation techniques, which allow you to track various properties so that you can actually scale the measurement system into the tens, hundreds, thousands, millions if you wanted to. Yeah. No questions. I'll give you a bunch. Here we go. This is the thing that makes it interesting. Given you've got these ideas now, if I get a delta Q and if I get this is where you could start to see how the issues of things like shaping and managing arrival patterns, which has already been discussed today, the effect of Netflix arrival patterns causes issues. You can now start to argue that you could deliver what's in a quality transport arrangement, right? A quantitative timeliness arrangement, right? Agreement that basically says, if you I will support your 4 megabits per second, but your burstiness, you have to deliver it in less than this burstiness, or in this arrival pattern, and I reserve the right to shape if you don't. Okay? Basically, at that point, you can show you're improving the service through the existence of the middle box. You could do so entirely mathematically. You have a hope of convincing the regulator. At least in Europe, you have a hope of convincing the regulator, given that regulators have looked at this stuff. Okay? And these, just like the Delta Q, these quantitative timeliness agreements, the QTAs, also compose. So you can create per hop supplier budgets, per hop supplier assurance, right? You're now in a position where you can start to construct on the basis of network layer transport assurance that supports assured application outcomes. This is what businesses would like. I would say what people want, for all those people on that train, if you ask them whether their Netflix was good enough, Dave, or what they really wanted, they'd say, I'd like glitch-free video calls, or I'd like things, I'd like my Netflix never to pause, and things like that. All of those are describable in these terms, and hence measurable, and hence possibly or well, you know, they could become something on which you could differentiate a market. Okay. The other thing it helps, instead of talking about buffer bloat, you could talk about assuring, minimizing the quality assurance, which applies to everything, not, implies to improving the loss, improving X, improving Y. And that gives you a dialogue. It gives you words, right? It gives you the right vocabulary. And it helps as people start to engage with the fact there is a trade, there is loss and delay. You can't have zero, depending on what you ask for, you have to control your demands in order to get the right supply. We have used this in the past to help people have internal dialogues, external dialogues with regulators, politicians, people like public customers, slowly building, slowly trying to manage the hype that occurs, right? And then it gets you the ability to create better solutions. Once you manage and know where the issues are, and when they occur, and why they occur, you can then work out why they occur, and then you can work out the appropriate mechanism to actually start managing the quality attenuation you generate, to try and get rid of it, or to share it out differently. And that's what every scheduling algorithm does. It just shares it out differentially. Okay. And you start to find, Dave was saying that you need to put Libra QoS as close to the end user as you can. Actually, I'd like, if once you've done this sort of analysis, we've helped people do it way away from the end user, because we could prove that the additional noise, quality attenuation, right, you're going to get was so bounded that the quality wouldn't be affected. And therefore, you've suddenly changed the economics of deploying your middle box solutions. You could basically incorporate it at the BNG, for example, in a broadband network, or in front of the CMTS, okay, or in front of multiple CMTSs. So I'm saying, and sorry, this is, I guess that this is this is how I think, this is what I think, but as people tell you, I also do. We also build things that solve these problems, measure and do it. But this is the framework in which we're doing this, right? We're basically able to measure the loss and delay characteristics through measurement. We can do it on existing traffic streams or with very low bit rate synthetic streams, and they are very interesting. They tell amazing amounts of detail, and you can start finding where equipment doesn't work properly, let alone for queuing algorithms. Once you can then drop that into relatively simple models, And it helps you create and test hypotheses as to whether what you would do and how you would do it. And we have worked with people whereby, having thought this through, they realize what they were about to spend money is the wrong place. They should be spending it somewhere else, to put the middle box, different types of boxes. And it stops, the aim here is to stop people creating solutions at the wrong places, right? And honestly, the simple solutions often work extremely well if you can just get them, if you can just not destroy the properties of the traffic stream afterwards. And create solutions. People have talked about solutions. People talk about measurement. People talked about solutions this afternoon. You need to solve the problem at the right place, because actually the place is not always where the problem is occurring. The place you measure it is not the place where the problem is occurring. If you can solve it upstream of that, you can save yourself a whole load of grief. Okay, I'm now basically at the end, I believe. I'm sorry, I didn't use up all my time, did I? I have no idea, Bjorn.
Very good timing, Neil. Thank you very much.
Questions, please. Any?
I don't see any questions in the Q&A at the moment. If people have questions, please do submit them. Thank you very much for the talk, Neil. I think we'll jump to the next speaker and then do the questions as they come in.
Okay, no problem.
All right, our next speaker is Magnus Olden, the CTO of Domos. It's a latency management company.
Have you heard of it?
We can see you and hear you, Magnus.
I'll start sharing screen. Okay.
We can see your slides now.
Perfect. Now even in presenter mode. So yeah, I'm glad I am coming directly after Neil, because a lot of the work I will talk about here actually is a derivative of a lot of the work that Neil and PNSOL and the Broadband Forum has done. So today I will talk about quality of outcome, QoO, which is an attempt to create a network quality framework that is useful for application vendors, for end user, network operators, and everyone pretty much. So see if I can go to the next slide. Yeah, so first I'm gonna do a bit of agenda. So I'll set the stage a bit, why we need this, why we think we need this, why it's focused on latency. And okay, so we are creating kind of a new, not completely new, but building some new pieces on top of some existing network quality framework. So we need to figure out why we're doing that and what our design goals are. So high level, we want it to be useful for everyone, like I briefly mentioned. And then we have proposed a solution based on the foundation of some of the work Peter has done, Neil and Peter in PNSOL and in Broadband Forum. And we propose something on top of that, but I want to make sure everyone, this is still a IETF ID, so it's still open for suggestion, complete changes. But what we are quite sure of is the design goals. And then from how we currently design it, I want to showcase some advantages of that. So let me just go right into it. So just zooming all the way out, what does consumer care about when they're using a network, right? They don't actually consume networks. They consume applications. They want applications to be snappy. They want the least amount of delay from when my voice is coming out of my mouth until it's in your ear, right? And I know it's funny using this kind of video in a slide over Zoom webinar because it looks kind of laggy for most of you. So that's an example of a poor application experience. But fundamentally, users consume applications, and the network is infrastructure that brings it. And network quality is really, really complicated, right? So that's why we have this webinar series. That's why, you know, we have no problem getting people on to talk about, you know, how difficult it is to measure network quality, all the ways we can measure network quality, all the dimensions of network quality, different kind of networks and network topologies, and, you know, sometimes it's multi-operators. Even as an operator, you don't own the entire path. We heard some CDN and app vendors talk about, you know, how they optimize and how different network layers optimize differently or have their own unique optimizations, right? And experience, you know, my experience of a network and my grandmother's experience in network is two very, very different things, right? So I have probably much higher expectations of a network than my grandmother does, right? So we have all these ways network quality is very, very complicated. So that's just kind of setting the stage. It's not easy. That's why we're all here. So this entire webinar series is about understanding latency. So I want to make a few points on, you know, why latency, why we focus on latency, and why that probably should be the starting point. So going back to apps, right? What do you care about in an app? You care about how snappy that website loads. You care about how quickly you can get 4K video on Netflix. You care about how long my voice takes to reach your ear, right? It's how quickly these apps function. That's what you care about as a consumer, right? And that is latency. Like how quickly you can get it there, that's the latency. So bandwidth is just a means to get it there, right? So bandwidth is a means to an end, but latency is actually the end in itself, right? So that's a foundational reason why we should focus on latency. Additionally, it has some other advantages, right? So if you have insufficient bandwidth, you will have poor latency because too much data will be tried to send through, it will go into queues, and you will have more latency. Yeah, but it doesn't work the other way around. If you have really poor latency, you can't observe that in the bandwidth or the throughput or utilization or whatever, right? It doesn't work that way. So starting from the latency side actually makes things easier. And that's my next point on this slide, right? Like we typically learn there are quite a few dimensions of network quality. You know, it used to be bandwidth, latency, jitter and packet loss. As you've heard throughout this webinar series, a lot of people are working on working latency, responsiveness, these kind of things, right? So the key thing, and you know, this is one of the key things Neil found out, is that if you actually measure latency distribution at specific load, you can actually capture all of these dimensions in a single metric, right? So if you have insufficient bandwidth, you will have increased latency. I mean, latency is obviously latency. Working latency are the higher percentile latencies, right? So all the way to the end of your distribution. And jitter is your distance between the high and the low parts of the distribution, and you can look at packet loss as infinite latency. Okay, but why do we need a new network quality framework? And the key point here is that we have all these technologies, L4S, AQMs, you know, FQ code, these and QoS techniques, and plenty of other techniques to improve latency significantly. Some of them have been in the market longer than other, but I mean, FQ code is what, 10 years old or something. It's still a lot of network equipment that does not have any active queue management at all, right? And what we're really seeing as what is holding us back, really deaccelerating, improving these application experiences, is not the lack of solutions. It is really the lack of demand from whoever is buying it, right? So it starts with the end consumer. They do not know that you probably are much better off with 100 megabits per second and an AQM than you are at 500 megabits per second and a FIFO queue, right? They have no idea. And it's really complicated right now to convey that message to anyone, right? So the lack of demand really stems from lack of awareness. So we want to make things simpler for even an end user to understand. So back to the design goals of the framework. Like, how do we make this network quality framework that is useful for everyone? So we have some design goals, right? So for the end user, we want a network quality framework that is honest and objective. We want it to be understandable, a key point, right? We want it to relate to what end users care about, which is application outcome, right? Because we want the end user to be able to say, how well will this app perform on this network? Will my Zoom webinar have high quality? That would be a really useful thing to know before I started this webinar. And likewise for the application, like if you're an application vendor, you want a network quality framework, once again, that's honest and objective, right? But you also want to be able to understand on a given network, either testing it live or even before, how well will my app that I'm developing work on this network, and how should I even adapt to that network, right? And that way it can relate to application performance as well, if it is possible to describe network requirements in this framework. And lastly, for network operators and vendors, again, you want this honest and objective part. We also want it to be useful throughout the life cycle of a network equipment, right? So for network operator, it's important to first do lab testing, then put something out in the field, do active testing while it's live, and then keep monitoring continuously. And then perhaps a point that is not very obvious if you're not in network operator or vendor is that you want some kind of composability, right? You want to figure out, so by composability, I mean, you want to be able to separate different parts of the network and figure out, okay, how much network degradation is each of the incoming bits, or the other way around, right? So for example, if you can measure the LAN side and the WAN side separately and add them together for an end-to-end network, you can both get an end-to-end measure, and you can figure out, hey, where is the degradation coming from, right? So how well will application perform on my networks, and how can we improve and troubleshoot it? So these are the design goals. So we have some proposed solutions. Both the design goals is in one of these ITF IDs, and the proposed standard itself is an ITF ID. And then there's also two open source versions of this in C and in Go. So how do we fulfill these design goals, right? So honest and objective across the board, everyone wants that, right? And luckily we can build on the work from Broadband Forum, which has done this, a strong mathematical foundation. Key point I want to make here is that we also want to make it probabilistic. Why is this? Because there is a lot of uncertainty in networks, right? So unless you can measure, say, the latency of every single packet and aggregate that and know everything about it, which you cannot for many reasons, you need to talk about probabilities, right? Because there is just no way you can ever say, like, this app will work perfect on that network and not on that network in a 100% sense, right? But you can say something about the probability, if that makes sense. And you want to be able to describe both complex networks and network requirements in the same framework. And you want to be able to test it in a lab, do monitoring, etc., right? And composable. Luckily for us, all of this comes from TR452 or QED, which I really encourage you to check out. But it lacks one part, like this understandable part. Like, how do we present this to end user? Because TR452 is really about these latency distributions and quantitative timeliness agreements and breaching them and whatnot and whatnot. It's a bit complicated, not for everyone, but for almost everyone. So we have this proposal where we instead talk about, okay, what is the probability of reaching different network requirements? So if we set up a network requirement for a Zoom webinar, for example, can we say something about the probability that my network will give a perfect Zoom webinar, right? We believe this is good middle ground between, the quality of experience measures, which are subjective, unreliable. You can't optimize the network based on some end users giving a video call 3 stars, right? On the other side, you have quality of service, bandwidth, latency, many forms and packet loss and whatnot, which is complicated. Like 42 milliseconds of jitter means very little to most people. But this network has 96 probability of a perfect Zoom webinar. That actually is quite understandable. I mean, it's still in this objective realm, right? So this is our proposal for quality of outcome. Okay, so how do we do this? It's a bit complicated, and I won't go into too much detail. It's all described in the IETF ID, but essentially you set up network requirements in such a way that, hey, Zoom webinar needs 5 megabits per second up and down, and it needs 90% of its package to arrive within 100 milliseconds and 99 within 150 milliseconds, which are what we call the network requirements for perfections. And then you also set up something we call network performance point of uselessness. Then you can measure a network based on the latency distribution while noting the load or the bandwidth. And you can essentially map this on, and there's a formula for calculating whether it's closer to perfection or uselessness. And by doing a few assumptions on linearity, we can call this a probability. So I wanted to talk a bit about why composability is important, right? So this is this idea that you can actually separate the network into segments, but still have a good statistical mathematical sum end-to-end measurement. And figuring out, okay, where is the quality degradation coming from? And this is a bit of what Neil talked about earlier. But essentially giving you this both top down, so you can look, end to end on the network. Hey, this video conferencing session has a 60% probability of a perfect session. Then you can also look at it bottom up. So like, okay, how much does each segment contribute to the network degradation? Is it in the operator's access or core network? Is it in the home Wi-Fi network? Is it even inside the device or from the ISP's peering point to the server, right? So separating into these pieces. This is just one example, but I want to highlight it because it gives you an idea about why this composability can be so useful for a network operator. They want to be able to understand where in their network or outside their network is this degradation actually coming from. And in Domus, we've actually built this into a product. So essentially in Microsoft Teams, you can download an app called Network X-Ray. And essentially it does two things. So it does both the top-down approach. So it measures the network quality in the context of the network requirements of Microsoft Teams. And essentially you can see what is the likelihood of a perfect Teams call end-to-end for each customer or each participant. And if you have our network X-ray diagnostics on your home router, it can actually surface a root cause analysis or recommendations. You can figure out, hey, how can I actually improve my network to get a better Teams call, which is using this bottom-up approach about figuring out which part of the network is actually causing this network degradation. So yeah, there is a lot more to be said here, but essentially I'll leave you with this meme, and we just want apps to work better. That's all I want to say. And once again, the IETF ID is very much open for suggestion contributions. So please be in touch.
All right, thank you very much, Magnus. We do have a question from Robert McMahon. I wonder if part of the lack of awareness and demand for low latency by users is due to the use of mobile phones, which fundamentally have high latency over mobile networks. you have any thoughts on this topic?
Well, it certainly sets some anchoring point, right? So this is what we used to, and this is how it works, right? That being said, like there are lots of work being done to make lower latency on mobile networks and Wi-Fi, which I'm sure at least Manny will talk about in the next talk as well. But yeah, I think it's even more, yes, so that's part of it, but it's very fundamental, right? Everyone is conditioned to think about bandwidth as network quality, that really being their only way of looking at network quality. Now we're already seeing a change around that. Well, at least quite a few of the US operators have now just completely stopped talking about bandwidth at all in their advertising. And we're seeing, both sides of the thing. So you see Google Fiber, who is talking about 20 gig fiber networks, but we're also seeing the other side, lots of the wireless ISPs, right, which is certainly will give you a much lower average bandwidth, but it's probably more than enough for most people in most use cases. And at that point, latency is what really causes the degradation, right? So it's an interesting question. I'm not quite sure, but I could probably guess for a couple of hours.
Yeah. Did you want to weigh in on that as well, Neil?
I just wanted to make a very simple point. I call this the Microsoft effect, right? It's the Windows effect. It's the Teams effect. We have been conditioned to basically accept crap software and crap experiences, right? And once you give people good experiences and try and take them away, they'll bite your arm off. So the real problem is in my family, where they all get good networking because hell, we try and make sure it is. They complain like hell when things don't work. In other places, they don't care, right? Because actually, it's just normal. So
Yeah.
I think he's right.
What you're used to certainly matters, right? Certainly, it sets the expectations, and
it is about expectations and aspirations. Then to maintain those expectations.
Yeah. All right. Well, thank you very much. We will now take a short break. 15-minute break or thereabouts until 1740 Central European time. So I will see you all then. Hey, Manny, welcome.
Hey, Aaron, how you doing? Can you hear me?
Very well. Yes, I can hear you, and I can see your slides as well. We're actually on a break right now, so your talk will start in about 8 minutes.
No worries. I just been queued up.
Yeah, cool. Right, so we're starting to approach the end of the break. Give everyone a little bit more time to get back to the computer, and then we'll get started very soon. Okay, so I'll introduce our next speaker, Mani Patel from Broadcom. He is responsible for the Wi-Fi access point businesses at Broadcom and will talk to us about Wi-Fi latency. So Mani, please take it away.
Hi, everybody. I want to talk. I guess the talk today is a bit about Wi-Fi and what ultimately are the contributors of latency over a Wi-Fi network. So I'll start here with this slide and talk about and break down the components of what we believe are the big contributors to latency over Wi-Fi, right? So channel access delays is one of the biggest ones in our view. And channel access delays fundamentally come from the fact that Wi-Fi is using shared unlicensed spectrum, right? So there's a contention-based MAC, which allows fair use of the spectrum amongst various wireless LAN devices, right? And that this contention-based mechanism ultimately creates some unpredictability related to channel access and can cause latency excursions if fundamentally due to the fact that multiple devices are contending for the same air. Another component of Wi-Fi that may be different from wired networks is that Wi-Fi is fundamentally half duplex, right? So it's the uplink and downlink are kind of time division duplexed for a lack of a better term. And so that adds another level of complexity and potential delays in round trip latencies, right? And then there's other aspects related to that can cause channel access delays, such as non-Wi-Fi interference, right? So if you have a wireless channel with non-Wi-Fi interference, that can potentially block the channel and delay the ability to transmit a packet over the air. And then finally, collisions, right? Even though the fact that there are mechanisms to share the medium fairly, you could, in theory, and from a probabilistic standpoint, get collisions in the air, which will result in packet loss and retransmissions, right? And again, this will also have an impact on latency. The second aspect of channel access delays is due to aggregation, right? In Wi-Fi, in order to get good protocol efficiency, there's this concept of aggregation where multiple packets are aggregated into a larger bundle, and then that large bundle of packets is transmitted over the air, right? And in most Wi-Fi implementations, right, you try and aggregate as much as you can, and usually the limit is 5.4 milliseconds of aggregation is typically the standard maximum aggregation that you get in Wi-Fi. So if you have, for example, a fully buffered download, you will typically see aggregates that result in 5.4 milliseconds of air being used on a given transmit opportunity, right? So this aggregation is essential for making efficient use of the spectrum. And then there's other aspects of aggregation called frame bursting, which are widely used in Wi-Fi implementations, which can result in sort of back-to-back transmissions without allowing for another device to capture the air. And when you're using aggregation, max aggregation plus frame bursting, you could get transmit intervals that are as high as 15 milliseconds, right? And then there's this another dimension related to service interval, right, where you are servicing multiple clients from a single access point. You have to kind of sequence through each device. And that service interval is going to be a function of both the aggregation, the frame bursting, as well as the convention that's happening on the air, right? And then the third aspect that contributes to latency, channel access delays, which ultimately contribute to latency, is client power management, right? In Wi-Fi, client devices, especially mobile client devices, go to sleep and then they wake up and receive packets. There's different protocols that allow you to that govern, when the clients go to sleep and how they wake up. But fundamentally, the fact that these client devices are going to sleep and then, waking up based on some sort of packet exchange based protocol results in additional delays in terms of being able to dequeue traffic to these client devices, right? So these are all things that are fundamental to the protocol and specification, but they ultimately create challenges with respect to the delays getting on the air and being able to transmit packets across the air, right? And then finally, there's wireless channel. There's just delays due to the wireless channel, right? And this could be the fact that the channel capacity is a function of time, frequency, and spatial variables, right? And what this results in is sort of the capacity of the channel can be highly variable in wireless, right? Shouldn't be a controversial concept. And the other aspect is that because it's wireless, the channel is lossy and it inherently requires retransmission. And you could get situations where even with retransmissions that packets don't get across the air, right? And so you get packet loss. And again, all of these things have an impact on latency, right? And then finally, wireless LAN is just another network node, and we have queues, and you could get queuing delays, as has been discussed during the course of the last couple of days, right? So queuing delays can happen in Wi-Fi, and they do occur, and that's another aspect that needs to get managed on a wireless LAN access point implementation. Okay, so what's happening? And often I get asked, what are we doing in the Wi-Fi realm to reduce latency, right? And what I would say is that it's a continual work in progress, right? There's been 7 generations of Wi-Fi, right? That have been implemented. The IEEE is working on the 8th generation, right? And there's a lot of legacy that you have to sort of deal with from a protocol and implementation standpoint. And so the other aspect is that in Wi-Fi you're trying to balance 2 things. One is speed and spectral efficiency, and that's largely a function of protocol efficiency, which is highly dependent upon aggregation. And then latency, right? And they can work against each other, right? So finding the right balance and finding the right tools to get high speed where it's needed, as well as low latency, is really what the standards bodies have been working on across these multiple generations of Wi-Fi, right? Now, if you look at what's being implemented in the Wi-Fi specifications over time, a lot of the focus has been there on reducing channel access delays, right? And reducing latency excursions due to channel access delays, right? And some of these things, I won't go through all of the alphabet soup of tools that exist, but some of the ones to highlight are obviously WMM, right? And folks that are familiar with Wi-Fi understand that there's these access classes that have been defined, which govern priority access to the air, right? And so there's some classification that's required in order to make sure that flows are properly put in the correct access classes. And this can help, prioritize traffic in a way where you can treat latency sensitive traffic appropriately and give it priority access to the air, right? In Wi-Fi 6, there was this concept of OFDMA and uplink triggering introduced. And what that allows is that the access point to more deterministically schedule both downlink and uplink traffic, right? Prior to Wi-Fi 6, uplink traffic, which is obviously important in terms of round-trip latency, was not in the control of the access point, right? With the introduction of Wi-Fi 6, the access point had the ability to fully schedule both downlink traffic as well as uplink traffic in a deterministic way, right? So this was a big step forward in terms of being able to have more deterministic scheduling of traffic and ultimately quality of service and QoE. In Wi-Fi 7, there was this concept of MLO, right, that was introduced, multi-link operation, which allows you to virtualize traffic across multiple links, right? So there's multiple bands in Wi-Fi, 2.4 gigahertz, 5 gigahertz, 6 gigahertz. The ability to transmit or receive on any of these bands is effectively what the multi-link operation concept is, right? And with multi-link operation, you can address channel access delays because you have the ability to contend on more than one channel, right? And because the contention is probabilistic, having the ability to contend on more than one channel allows you to get statistically a higher chance of getting access to the air. And then in Wi-Fi 8, which is currently in progress from a standards perspective, there's a number of other things that are being looked at from a protocol standpoint to reduce channel access delays, right? So this concept of preemption, which is to deal with those long bursts of traffic that we have in Wi-Fi, right? As I mentioned, you could get bursts as long as 15 milliseconds. And the idea with preemption is that, if there is a long burst happening, and then a latency sensitive packet is at a head of queue somewhere, you have the ability to sort of preempt that long burst of traffic and transmit the latency sensitive packet sooner than you normally would have if you didn't have preemption. Okay. Now, what I will highlight here is that all of these tools, and there's more tools than I've mentioned here, they all require three fundamental things. One is traffic classification, right? We need in Wi-Fi, we do need to understand, what the nature of the traffic is, right? And there's these access classes that I mentioned, which are kind of defined as background, best effort, voice, and video. Those are sort of kind of high-level access classes that we have as tools to use to govern access to the air. And then there's also this concept of latency sensitive versus latency insensitive traffic, right? And I think these classifications are very important in order for us to use the tools that we have within Wi-Fi efficiently and properly. The other requirement is traffic separation, right? You can get into situations where you get head of line blocking, and the fact that we have the shared medium that we need to kind of manage between both downlink and uplink requires traffic separation in order to sort of get the proper quality of service, right? And once you have classification and traffic separation, then things come down to optimal scheduling, right? So the scheduler within a Wi-Fi access point is very key in terms of ensuring that ultimately at the end of the day that you are able to kind of manage both speed as well as latency and ultimately quality of experience for the end users. So the scheduler implementation is a big part of the overall solution, and effectively the scheduler uses all of these tools in addition to the traffic separation and classification in order to get low latency as well as high speeds. Okay, a little bit about the evolution of queuing architectures within Wi-Fi, right? So if you kind of go back to the 802.11b days, right? Effectively the first widespread implementation of Wi-Fi, all of the traffic was effectively in a single queue, right? So everything would kind of get no matter how many client devices that you had out there, most of those implementations back then required everything to be in a single queue, and there wasn't even access classes back there because 11b predated the WMM specification, which allowed you to kind of have the sort of priority access to the air based on access classes. That came in 802.11g, right? So, but even in the 11g implementations, most of all of the traffic was still in a single queue, right? So you would have a shared queue, no matter again how many client devices that were out there, and then you would have this ability to sort of based on tagging be able to put traffic into prioritize traffic based on access classes down in the lower MAC. When you got to 802.11n, you got into more advanced queuing implementations where you started seeing the introduction of per client queues. Okay, so with 11n, many of the implementations started separating traffic into separate queues based on the end client devices, right? So client 1 would have a unique queue versus client 2, and all the way up to client n, right? You would have separate traffic separation based on client devices, right? But then in the lower MAC, everything would sort of, there would still be a point where everything would kind of get put into the 4 access classes, the background, best effort, voice, and video. And so you would have sort of a headline blocking issue in even the 802.11n implementations. In modern Wi-Fi, what we have is implementations where there's traffic separation all the way down to the air, right? So you have per client queues, and then you have queues that are, each client queue is separated into its own access category, right? So, if traffic is categorized for client 1 as best effort, that would be in a separate queue from, let's say, a traffic that's targeted for client 1 that is categorized as a video, right? So you get this sort of very discrete traffic separation in modern Wi-Fi implementations. And what this effectively does is it allows you to largely eliminate head-of-line blocking, right? And then the scheduler between the software scheduler as well as the hardware scheduler in the lower MAC use the various tools available. And again, there's a list of things that I already discussed that manage access to the air, right? And obviously, if you have an understanding of whether the traffic is latency sensitive or latency insensitive, whether the traffic is sort of a bulk download versus a Zoom video stream, right? The scheduler the schedulers by using the tools that are available can provide priority access to the air for, let's say, latency sensitive traffic, right? And then allow latency insensitive traffic, let's say like a download, to build up buffers to make sure that when you transmit it over the air, that the speed and aggregation is high enough where that ultimately you get the fastest speeds possible, right? So with these modern architectures that you have on the queuing side, you end up reducing and potentially eliminating a lot of the queuing delays or buffer bloat, right? Because of traffic separation, as well as classification, and then ultimately prioritization. I want to give you guys a bit of an example of what I'm talking about with respect to channel access delays and then things that we can do to address those channel access delays, right? So this was some data that was taken where you had a Wi-Fi network with a single latency sensitive flow to a single client device, right? And then you had 4 overlapping networks that were using the same channel as the access point under test. And then what we did was we varied the network load on the overlapping networks. We call in the Wi-Fi world, we call them OBSSs, right? And you can see on the graph on the left, and specifically look at the sort of light blue line, the one link graph. As the network load on the overlapping networks increase, right, the latency for the device that you are interested in increases substantially, right? And this is largely all due to channel access delay, right? So it's 100% due to channel access delay. Now, as I mentioned earlier, in Wi-Fi 7, there's this technique called multi-link operation, which allows you to transmit packets on multiple links, contend on multiple links, and transmit packets on any given link available, right? And what you can see here is that, you know, if you are able to use two links instead of one link, which is kind of the one link scenario is what has existed in Wi-Fi 6 and prior, right? In Wi-Fi 7, we have this concept of being able to transmit on multiple links, and you can see that when you transmit on two links, worst case latency is greatly improved, irrespective of the network load on the OBSSs, right? And then if you have the ability to transmit on three links, you can see that latency improves even further, right? And so this is one example where we don't have any queuing delay here because there's only one flow. There's no queues that are being shared here. And the entire delay that you are seeing with respect to the poor latencies is largely driven by overlapping networks that are active. And the way to go address that in the Wi-Fi world is this concept of multi-link operation, which allows you to potentially contend on multiple links, allowing the latency to greatly improve. The graph on the right shows a little bit of a different scenario where we increase the number of client devices on the access point under test from 1 to 4, right? So there was 4 client devices where we were transmitting latency sensitive applications to. And then you still have your 4 overlapping networks with varying network loads, right? And you can see that when you have 4 devices, right, the latencies get significantly worse. The worst case latencies get significantly worse, irrespective of the network load, right? But again, multi-link operation, and the reason things get worse with 4 client devices is that you have not only channel access delays due to the overlapping networks consuming the air, but then you also have channel access delays due to service interval and scheduling within the access point under test. But irrespective of that, multi-link operation, the ability to kind of contend on multiple links and use multiple links has a dramatic improvement, provides a dramatic improvement in worst case latency. You can see that, you know, there's, you know, in the 100% utilization case where the airtime is 100% utilized by the overlapping networks, you can see that the latency falls from, you know, a little bit under 300 milliseconds down to, you know, 25 milliseconds or so with the use of 3 links. Okay, so to conclude, right, and, you know, what are the takeaways? We believe that in modern Wi-Fi implementations, latency excursions are dominated by channel access delays, right? And in order to solve those channel access delays, you need prioritization and scheduling. And in order to do prioritization and scheduling, you need classification and traffic separation, right? So if you have all 3 of these things, classification, traffic separation, prioritization, scheduling, we believe that, you know, both speeds as well as latency can be managed quite well over Wi-Fi links. And then, you know, a side, you know, benefit of having traffic separation and classification is that queuing delays, especially for latency sensitive flows, are largely minimized. And I think we see that in modern, in at least in our modern Wi-Fi implementations. So I'll stop there and take any questions.
Thank you very much, Manny. That's super interesting stuff. We are a bit over time, so can you please use the Q&A tool to answer the questions in writing? And then
Sure.
we'll jump to the next speaker. Okay, thank you very much. All right. Our next speaker is Michael Welzel, who is a professor at the University of Oslo. And he will be talking about making buffers larger for some reason. And I promise he's not crazy. So here you go, Michael.
Okay, can people see?
I can see the slides and I can
Slides?
hear you and see you.
Okay, this is all good. I'll just make you all a bit smaller. All right. Yeah. So this has got to be a little bit crazy. I'm an invited academic, and I think as an academic, I have that role of not showing workable solutions, but provoking you to do crazy things or think differently about things. There is also the advantage of this being a webinar where you cannot throw vegetables at me. So I'll speak very freely about these things. Here's a motivating problem for what this is about. It's not, what I'm going to talk about is general. It applies to all kinds of networks and situations, really, but it becomes very obvious when we consider links where the capacity fluctuates, like millimeter wave links, and we're going to have more of these kinds of things like sub-terahertz communication, visible light communication, and you see these pictures here. These are taken from a paper, not our paper, that highlight how the capacity can fluctuate greatly in millimeter wave communication. And the problem that we have with this is that a congestion control mechanism, by the way, this is probably the right point to apologize to Stuart for using that term. I am a big fan of this, of his proposal of, for instance, removing that particular name and calling it, what was it, rate adaptation algorithm. But I'll stick with the terminology that I'm used to now to keep this clean and simple. So a congestion control mechanism is going to be able to detect that capacity has dropped and it needs to reduce the sending rate. But if the capacity suddenly increases, well, we have to do something, right? There is no immediate information back to a sender to say, go up, increase your rate, or, and there have been plenty of ideas on these kinds of things over the last couple of years in papers, some end-to-end, which are a bit slow to react. People have come up with ideas to signal an end system from a device inside the network that has various issues regarding standardization. Some ideas were related to putting a proxy into the network, performance enhancing proxy, and that may be the best of the bunch, but it has also issues in reaction speed. Again, I'm trying to stress here that this is not only about millimeter wave. It's, whenever you have any kind of traffic fluctuation, which can happen due to even other traffic coming and going, or mobility, what have you. So we can sketch a pretty ideal example of what we could do. If capacity has dropped, the congestion control has reacted. Like here, capacity goes down, then capacity becomes available. You could have a signal from, let's say, the millimeter wave access point directly to the sender to say, go slower when it goes down, and when it becomes available again, you will say, go up. And the issue that I really focus on in this talk is that the data, ideally, at this point in time, should already be at the access point. So any signal that we come up with to tell the sender, you should increase your rate fast, well, it's going to come with delay even just for the signal to reach the sender, but then the sender needs to ramp up in some congestion control fashion, figure out what the right sending rate is. By the time the data reaches the access point, capacity may already become, may have declined again, and it may be too late. The real issue is that the access point doesn't have data. Now, storing more data at the access point is usually perceived as a trade-off because, well, if you store more, you have a larger buffer. A larger buffer harms latency, but we need low latency. Well, what I'm trying to tell you here is that this is actually pretty often not a trade-off. And there are applications, and more than you may think, that can benefit from a huge buffer, actually. So if we take a step back and consider this as just a fundamental thing, imagine a single application alone in the network, nothing else, right? We make this very artificial and fundamental. In the case of one application wanting to get data from a sender S to a receiver R via intermediate nodes A, B, C, D reliably, the fastest thing that we can do is to buffer data. Because if data becomes dropped for some reason, if C, for instance, cannot immediately forward it because there's no capacity available, it is faster to have the data in C and to immediately send it when capacity becomes available, rather than dropping it and asking the sender to send it again. And faster is another term I shouldn't be using according to Stuart, and I completely agree with him, but I haven't updated my presentation to fit that. Anyway, getting it from S to R faster, that means lower latency. So I'm talking about a case where we buffer more data and reduce latency, which should provoke you to start thinking about what latency really means for users. It is lag when we interact with a computer or via a computer, right? I'm using a game or something via a computer. Well, now, if you talk to me, there is possibly lag and me reacting to you. And this lag means different things for different applications. So I would like to talk about two application types. One is the application type that we have, mostly focused on in this online webinar here, which is things like video conferencing, game, remote control. This makes me think of Stuart's great example of screen sharing that he had several years ago, where his point was that if you want to be interactive and an interactive application should see little delay, you want to minimize even the buffer in the sender host. Now, indeed, this is a case, all these cases where an application is interactive and you need something to react upon the other side doing something, they need the sender to be in control of the data until the very last moment. So you do want all buffers from the sender application to the receiver to be as minimal as possible. However, there's a whole other class of applications which also can be what we sometimes call latency critical or low latency. And these are applications that care about the completion time of a data transfer, the flow completion time. The typical example would be web surfing with static content. So if you want to try to get a static web page from A to B, the difference between this type of application interaction and the other type of interaction is that the application wants to get rid of the data as soon as possible and doesn't actually need to stay in control of the data. This is the case for also distributed computation applications. Anything that is really a request response type application, to some degree, can also apply to HTTP adaptive streaming, but that complicates things a little bit. I'm not getting into that. But basically, web surfing with static content, if a single application in the network would benefit from a large buffer, and it would be faster. And from the point of view of the user, that is the case where I click on a link interactively, I click on a link and I get a result. So the interaction has become quicker. And this is what we usually would call lower latency. So in the case of the first category, the metric is the per packet latency, whereas in the case of the second category, the metric is really the flow completion time. That is what dictates what we perceive as latency as users. Okay. Yeah, so I want to stress that as well. These applications that benefit from a large buffer, we could be talking about a huge buffer in the network, just the application by itself. About time to get back to reality, right? For some applications, we should, in theory, be able to reduce latency by adding queuing. However, in reality, applications are not alone in the network, and end-to-end congestion control does not cope well with very large buffers at all. And what I'd like to claim is that for the sake of being able to introduce large buffers for reducing latency, TCP connection splitting PEPs almost do the right thing. They almost give us what we need. These are devices that would lie to a sender and say that they're the receiver, and they would lie to the receiver and say that they're the sender, spoofing IP addresses, and then you have split the connection into two pieces. What that does is it breaks an end-to-end control loop into halves, and it has per application buffers, which of course has scalability limits. And then these devices have been known to introduce all kinds of problems. But because they cheat TCP, because they spoof IP addresses, they can cause network ossification. Because they're not chosen by the application, there needs to be a trade-off in how much data we can buffer, because the proxy cannot really reliably know what kind of application it is. So PEPs actually have to implement a compromise here in their buffers. Commonly, this is done using the receiver window, where they tune how much they accept from the sender. Also, they implement reliability. They need to, because an ACK in TCP tells the sender that the receiver has gotten it, and that also causes various other problems that we may not want for such a device. So ideally, what I claim we would like to have as something that could make things better would be a device, a proxy that is a bit like a TCP connection splitter, but it would be explicitly chosen by the application only for short completion time applications. And then this PEP could carry out the right task. Now we can already do this for Quick. This is kind of a side note because I'm not getting into the details. There are two papers. There's one paper that's already published and another one that was just accepted for NSTI using this thing that we call a sidecar. If you want more details, well, the first paper is available and you can always get in touch with me. I'm happy to talk about it. But that would sidetrack too much. Anyway, the functions that are needed in such a PEP, in this hypothetical PEP I'm envisioning here, would be to protect the interactive traffic from the short completion time traffic. Clearly, we'd never want to harm interactive traffic with large queues. Then probably also protect the short completion time flows from each other. Again, this could be heavily unfair if you have large queues and then you need to deal with multiple applications. And perhaps we could even use it to give a higher priority to interactive traffic, because now we're making the short completion time traffic complete faster by serving it a large queue. And so in that sense, the scheduler could, it could be tuned to even prioritize interactive traffic. So this is all ongoing work. This is all very, very early research, but I do have one experiment to show you. We tried to build such a system as an extension of our own TCP connection splitter that is called PEP-DNA. It's an open source thing that we have. There's a previous paper where we have some details about it. It's a kernel space TCP connection splitter. And in our version of that, the sender chooses this service. So the sender makes a conscious decision to pick this proxy. It's done with connection setup following the 0RTT convert protocol that is in RFC 8803. Essentially, you have an option in the SYN telling the proxy that I would really like to talk not to the proxy, but to the real end. And then the proxy takes that information to immediately connect you to the end. We carried out tests in a 3-node testbed using 2 flows. And in the intermediate node, the router, Linux router, we had this PEP-DNA software, and underneath we have the default queuing system, which is FQ-CODL. The category 1 traffic is the voice over IP traffic, we call it. It's just artificial traffic of 20 packets per second, small packets, 100 bytes, that mimics Skype, at least according to a paper I found. And category 2 would ideally be a cloned web page and then web surfing with the end goal being that we could show that web surfing can go a lot faster without harming the voice over IP traffic. Now, as this is only the beginning, instead we use the file transfer to see what we can do. The link between the sender and the router is 100 megabits with 100 millisecond delay in one direction. So it's 200 in the round trip time. Sorry, it's only configured in one way. So it's this delay, and there's the router receiver link with 20 milliseconds. So we have roughly an RTT of 120 milliseconds. And the router receiver link has 15 megabit. And as capacity suddenly becomes available, after 18 seconds, there was a configured thing to make the diagrams look interesting. the capacity jumps up from 15 to 70 megabits. And well, it's one first experiment. Again, the goal would be to get web transfers to run faster. So here's a result of doing that. What you can see here is a blue line in 3 different cases. The blue line is the voice over IP flow latency. The top diagram is the end-to-end case with the TCP FIFO queue, and the middle one is TCP with FQ-CODL. The lowest one is our system. The red line, the first red line is when the file transfer begins. The second red line shows you where the bottleneck capacity was increased from 15 to 70 megabit per second. And what you can see is that as the file transfer ends, that will be the third line. Well, it takes quite a bit. You see this sawtooth in between where TCP is increasing the window and causing delay for the voice over IP flow. Now, with FQ-CODL, the queue that's given to the data transfer, to the file transfer is a bit shorter, so that takes a little bit longer. And with our PEP, we cut the file transfer completion time by 5 seconds. So it's faster than even 5 seconds compared to the FIFO case, and a lot compared to the FQ-CODL case. And what we hope to achieve would be that the blue line looks just the same as with FQ-CODL, because, well, it is FQ-CODL. It should separate the two traffic types. We get this surge of delay while the PEP pulls the data from the sender, and we get tiny delay spikes afterwards. This is not really much, but it's a little bit. Actually, frankly, we don't know where that comes from. We did expect FQ-CODL to prevent it. So what we're facing is traffic that is being forwarded as opposed to traffic that essentially comes from the same host. It is in the kernel, but I think the way this is operating in the kernel, it's still from above, a bit like traffic coming from user space. Because of this feedback system in the PEP with byte queue limits at the NIC and TCP small queues before the queuing system, we would have expected that this traffic does not cause extra delay for the forwarded traffic. Maybe it's somehow prioritized when it's local, we don't know. What we found also with multiple file transfers in parallel is that the PEP is always a great gain for the file. This is the final slide of data. The diagram on the top shows you the the flow completion time of the file transfers. It's a violin plot for the end-to-end case. Because it's multiple transfers and we carry it out each 10 times. So you see a distribution here. Whereas the case with the PEP is just the blue star, because it was always the same result and all the flows had perfect fairness, because really the PEP was able to get all the data before capacity increased. And from then on, everything was just fed into the FQ-CODL system with perfect fairness. And then, it's from there to the receiver. So there's no real distribution here. It was perfectly fair, and reduced the flow completion time by multiples of seconds. Now the diagram on the bottom shows you for the cases of 1 to 10 connections, 3 things. The first is the UDP latency in the end-to-end case, which is minimal. And then the second, there is P1 and P2. This is just me cutting the file transfer into 2 parts. P1 will be the first half, which includes the part where the data comes to the PEP. And P2 will be the second half where the PEP already sits with all the data and is just forwarding it. And we see that there are some outliers in case of P2, but it's really not much compared to to the end-to-end case. But it's quite a bit more, 1-2 milliseconds or something like that on average in the P1 part, and we don't really understand where that comes from, but this is ongoing research. We expect it to be solvable. My conclusion is that just shortening all buffers, even dynamically, even using an AQM algorithm, is not in principle always the best solution. Actually, short completion traffic can be latency critical. There are things like web surfing that we perceive as latency critical, but this is traffic that wants a large queue. So I'm essentially trying to tell people that there is not just latency critical traffic versus bulk data transfers. That is the wrong classification. It's not easy to begin making buffers large again without making things worse again. Benefits can be large if it's done right. We suspect, at least it seems like it. For short completion time applications, the buffer size is not a trade-off, right? If it's done right, but it's difficult to get this right. This is all early stage ongoing work, and that's it. Actually, with questions, before you ask me questions, if any of the latency experts here would be able to answer my question of where our latency comes from, that would be fantastic.
All right. Thank you very much, Michael. Please do the Q&A using the built-in tool. I think there are a few questions there.
Okay.
Because we have to move to the next speaker. Thank you very much, Michael.
Yeah, thank you.
Our next speaker is Lai Olsen from a measurement lab, where she's a data scientist and researcher, and she also leads the Open Internet Performance Measurement, and she's a professor at the New School. So please, Lai, I can see your slides and I can see your video.
Okay, last check. Can you hear me?
And now I can hear you as well.
Okay, wonderful.
Excellent.
Okay, we did it. It's always a test. So hi, everyone. My name is Lai. I'm representing Measurement Lab today. I have the slides linked here. I'll also just drop these into the chat. This is not the bit.ly link, but it will do. So my goal today is just to introduce MLab to those of you who are not familiar, although I do see a lot of familiar, not faces, but names. So for some of you, this will be review, but then also wanting to basically introduce some open questions that we have and thoughts on how our data can be useful in this space. So unlike other presenters, I'm not necessarily presenting research, but opportunities for more. Okay, so
Lai, I just want to
yep, go ahead.
point out that the aspect ratio of your slides makes them a little bit small on the screen.
Got
I
it.
think
Okay.
you're just sharing a
How about
window
this?
that is, yeah, that's much better. Thank
Okay,
you.
great. Thank you so much. Cool. So just for history and context, we were founded in 2009, thinking about the question, how do we measure internet performance at scale? So folks here are familiar. A lot of times we collect data on a pretty small scale to either test things, prototype different protocols, et cetera. But the question was, how do we do that on the real internet? And again, across the network of the internet at large. So a bunch of researchers from New America's Open Technology Institute, Princeton's Planet Lab, and Google came together to create the consortium that we have today. And what that's led to is an organization that has the mission to measure the internet, save the data, and make it universally accessible and useful. We are also a fiscally sponsored project of Code for Science and Society. So another thing that led to is basically this big platform that we run now that has a presence in transit networks as well as cloud providers as of 2022. Our servers historically have always been placed in interconnection points, so places where ISPs peer with one another, and then, like I mentioned, also in cloud providers. Side note there, we are actively looking for presence in more cloud providers. So if that's something that you or your organization are interested in, basically being able to provide open data that has your provider represented, that's something that we're looking for. So where that's led us, though, is having about 750 servers globally in about 70 metros, 40 countries, 50 transit providers. I can send later the link to our infrastructure map, but basically a global presence, although we can always have more. And that platform would not be interesting unless it did something. So on that platform, we host what we call measurement services that produce the data that I mentioned before. So probably our most well-known measurement service is Network Diagnostic Tool. From this test alone, we've collected about 6 billion tests over the years, and about 4 million tests per day come in on average. So there's just a lot of data. What NDT measures specifically is single stream performance of bulk transport capacity. This is often conflated with the speed test. I have more to say about that later, but people commonly refer to it as a speed test. And the reason, or a good portion of the data that we take in comes from the integration into the Google search page. So a lot of our data comes from there. specific to the conversation today, our latency measurements is reported by the last min-RTT sample from TCP info. We also collect TCP info metrics. And just for reference, if it's, I'm assuming it's been talked about today, this is not what we would consider loaded latency, but that's something that we are interested in implementing and or hosting another measurement service that could do so. NDT is just one of 12 slots that we have on the platform to host measurement services. So if you have something, if you have a measurement tool that you're interested in seeing how it can scale and collect data in the internet on a global scale, that's something that we would be interested in talking about. Also, perhaps interesting to this group, we have recently developed over the past year a tool called Measurement Swiss Army Knife. It's titled this, or it's named this, because we think of it as basically configurable NDT. So NDT, as I mentioned, measures a single stream. I didn't mention this, but it uses BBR as its chosen congestion control algorithm. Measurement Swiss Army Knife is developed to essentially make those options configurable. Over the years, we've heard feedback that multi-stream is something that people want to be able to use to perhaps get closer to link capacity. So NDT is able to have a configurable amount of streams to be used, as well as a configurable congestion control algorithm. So BBR or Cubic could be used. Something that we're working on is also being able to configure the amount of data that is sent. It measures UDP-based latency, and this was to fit the requirements for those who wanted to use a version of NDT or a speed test in the FCC's mobile broadband data collection program. The FCC specifically required that it be a UDP-based latency test, which is perhaps also worth discussing here, but all to say that's why we chose that. And we have a Go client and server available right now. And our goal is to have our speed.measurementlab.net running Measurement Swiss Army Knife in JavaScript by early 2024. So would be happy to discuss that if people are interested in using this tool as well. Also worth noting is that for every test that is run on the platform, so this is NDT or otherwise, or any other service, we also run a trace route that collects, the network path back from the server back to the client, as well as PCAPs and TCP info data. And all of this data is published in BigQuery for open access, which I'll touch on a bit later. And interesting as well, as of this year, we're also starting to run, well, we've always hosted reverse traceroute since I think about 2019 or 2020, which of course tries to estimate the path back from, in our case, the client back to the server. And we are starting to run this as a sidecar service as well, meaning that soon we'll have essentially for every NDT test or every MSAC test or any other test, we'll also run a trace route and a reverse trace route. So an open research question that I'll talk a bit more about later is thinking about looking at any NDT test and being able to also look at the two trace routes in both directions and see if there's anything to be gleaned from the information there regarding latency. Also worth mentioning is that we also publish third-party data, including Cloudflare's speed test data and AIM data. So speed.cloudflare.com is another speed test. They also measure loaded and unloaded latency, and we publish this data. So this is currently available for open access. And alongside that, we also publish the AIM data, which is essentially, as someone from Cloudflare might have already talked about this, but assigns point values based on what your speed test results show, such that you can understand, and you being a user can understand how well your internet works for different use cases, such as streaming, gaming, and video chatting, or Zooming, I guess is what we might call it. And again, noting that it includes latency under load metrics as well. Also worth mentioning that another measurement service that we host is WeHe, which is led by Dave Chofnes at Northeastern University, which essentially is an attempt to measure net neutrality on an application level. So it emulates traffic going to different content providers and attempts to detect whether or not the traffic is being treated differently based on what content it's transferring. So we publish the data from this measurement as well as host the server side. And so I think I'm zooming by, so I have some time. The research questions and projects that I wanted to bring today, just to kind of invite people to think about, maybe propose projects around, or just talk to us about. As I mentioned, we published the loaded and unloaded latency metrics, and I think there's a lot to be explored there. As far as I know, no one's really dove into that data, so I think that's really just sitting there to be looked at. I believe we've been collecting it since October 2022, so about a year's worth of data, collecting both loaded and unloaded latency, so that's available. Also thinking about, as I mentioned, reverse traceroute, and NDT. Part of this is us recognizing that a speed test can only tell you so much, or I'm going to do quotes around speed. And perhaps there's an opportunity to give more context to what an NDT test tells you if you can also look at the different pathways that the content has taken. And then this is, I think, kind of the sort of larger purpose of the conference, Understanding Latency, is thinking around how can we move beyond speed tests and what metrics should actually define internet quality. So this is something that we're going to be pursuing through an Internet Society research grant, thinking about what are the different metrics that if a region or a country wants to be able to assess their internet quality, and particularly throughout time, what metrics should go into that assessment. There's a lot of different efforts that I'm sure have been represented today, such as Apple's responsiveness metric and Domos's as well, quality of outcome, also Cloudflare's AIM metric. These are all kind of attempts to move beyond the speed test. And so we're really interested in being able to capture that in a way that decision makers can understand and make use of. So this is even acknowledging that we're one of the largest speed test providers, trying to think kind of beyond just that one metric of throughput and bandwidth, and thinking about how metrics like latency and all of its forms, packet loss, jitter, et cetera, can be well represented to the general public. So these are kind of three ideas for how our data can be useful. I also hope that you come up with many others. And beyond that, as I mentioned, if you're interested in hosting or providing a measurement service for our platform to collect even more data or other kinds of data, that's also something that we would be interested in as well. Just to wrap this up and kind of give you the entry point to being able to do any of the research I previously mentioned. If you're interested in using the data, it's really easy to get access. You essentially just go to our website, click on data, and then there's a BigQuery quick start. From there, you can sign up for our Discuss email address mailing list, and this will get you access to the data. Again, it's upwards of 6 billion rows, so there's a lot there, and you will not be charged for access. And then you then can interact with the data through BigQuery. We also often use Jupyter Notebooks, and getting more accessible visualizations is a top priority of ours. So if you have thoughts on how the data should be represented or what would be useful to see in terms of insights and ongoing analysis, definitely happy to talk about that as well. And I can take questions now if there's any.
All right, thank you very much, Leggy.
Thank you.
We do have time for at least one question. So Neil is asking whether you're aware of the Broadband Forum's TR45 2.1 measurement approach. There's a quote attenuation or QED framework from the Broadband Forum.
I'm not. I'm only a little bit aware of the Broadband Forum itself, so I would like to know more, and we can maybe follow up about that.
Sounds good.
And oh, let me actually, sorry, there's would there be an appetite for hosting observers or reference points for that measurement approach? Would obviously have to read more about that measurement approach, but in general, yes, this is very much something that we see ourselves as our contribution is providing different vantage points, both from the client and the server. So yeah, I would like to follow up about that.
Right, excellent. Thank you again very much. We will
Thank
move
you.
on to our next speaker, who is Kathleen Nichols, and she will talk about the CODL AQM. She's one of the original authors of that, and I hope to learn even more about it. So Kathleen, whenever you're ready. There we go, your slides are coming up. Now we can see you and hear you.
Okay, all right.
Excellent.
Wow, and I actually succeeded in getting my preview window through, right?
Yeah, the slides are
Okay.
not up yet.
Oh,
For some reason.
I thought they came up a minute ago.
It
All right, go
just
back.
says that you've started the screen sharing, so it's
Oh, we had this problem before. Okay, I may
yes.
have to do something suboptimal then. Okay, back to share. Okay, I'll say cancel. Share. It doesn't like my PDF. Let's try this. Did that work?
Yes, that does work.
All right, well, I'm just going to do it from here and see how that works. Okay, so what I'm talking about, I want the emphasis on, why do we control delay? And the, go over here. And I wanted to say that unlike the other talks here, this is focused on work that was done in like 2011 to 2012. And back then, most internet traffic used Reno or Cubic. There wasn't any Quick. And I think surprisingly, there's still some relevance. Plus, Bjorn requested that I talk about this. So I feel like I'm going backwards in time. But so my contention is that AQMs and transport protocols and other elements in the packet path should really focus on controlling delay. And there are two main reasons for that. One is because internet traffic is not Poisson, and that delusion led to many years of people trying to control the queue length. And but it turns out, of course, that delay cannot be inferred from queue length. And if you want to know more about that, you can see these references, or you can especially look at Van's rant on queues. It's from like 2005, I think. And I think that the CODL article that we did in CACM and RFC 8289 say some of these things well. So in this talk, I'm going to focus more on kind of motivational and trying to, what headspace am I in, and see if maybe some of you can be in that same space. And the other reason we should focus on delay is because that's what makes users tear their hair out. And I think that's kind of what the people focused on applications at this seminar have been talking about. And also, I want you to realize that delay is a universal thing. So if we turn things in the network into delay, then the amount of delay that users will accept is something that's been studied. And delay has bounds. There's upper bounds on delay, and things start to die. And what I mean by that is it's delay that's important, not number of packets. Once we get beyond silly things like we have to have enough packets. So this is kind of a review, and since Neil covered this sort of thing nicely on Tuesday, I can be quicker about it. So the full buffer problem is something that has been known for a long time, and that mainly results from transport protocols trying to fill the pipe between the source and the destination by increasing the number of packets that are in flight until the sender gets some kind of indication that the pipe is full. Usually it was a drop. And this is, this was called the full buffer problem long before Jim Geddes taught us all to say buffer bloat. Unfortunately, the pipe here, it means that you fill up all the buffers all the way along your path, and you form this persistent queue of packets of however many your window for your protocol will support and are in the buffers. And then those persistent queues mean that you have this added delay, which latency, that doesn't really have any benefit. The data doesn't come to you at a higher rate, and instead you've got these full buffers that don't leave any room for anyone else. Something else tries to start up and it gets dropped. And now we all use this nice name buffer bloat for the full buffer problem, which the other nice thing Jim did was make people start to pay attention to it again. So here's my picture of the buffer bloat in action, and this is kind of fun. And I took this with Passive Ping back in 2016 on my laptop. And if you look, you can see I was looking at the round trip delay, and look at that, everything was up above 200 milliseconds and going up towards a second. And then suddenly it dropped down for a while and then it went back up. And, I could zoom in on this and look at the delay going to Netflix, and you see this characteristic where Netflix is sending, each burst of traffic, and they have very long windows, and they aren't, they're just kind of opening things up, fill up the pipe, and there it goes, delays over a second. And those are seconds on the side there. Okay, so the internet has these packet buffers to handle the normal burstiness of statistically multiplexed networks. This is good, right? I think Neil mentioned this kind of thing. But the persistent or standing queues of packets develop wherever we've got fast to slow transitions, or can develop. And this is bad if they hang around. And this picture shows things are coming in on the fat pipe and they don't take up very much room in time. They go into their waiting room to wait for the skinny pipe where it takes more time. And if we transform our packets into time at that point, then at the DQ time, we want to know how long each packet spent in my buffer, which is the sojourn time. So what I want to emphasize here is that back in 2011-ish, I was looking at this like, what can I do about this problem from the point of view of a buffer? And that's usually what we think of as AQM, right? That's what we do from the point of view of the buffer. So if I'm a buffer, the only thing I can do is make sure that things don't hang around in my buffer too long. On the other hand, I don't want to mess up the good queue that absorbs the burstiness that might be coming through, that say in that fat pipe, a clump of packets, a perfectly reasonable clump of packets arrives, but it has to take some time to go out on the other side. But it doesn't do any more, that clump may not do anything more than fill up the pipe and doesn't overfill it. In that case, I don't want to drop it, right? And I just did a little bit of arithmetic here to point out that, if we think just about packets, they all have very different timing. And back to this idea that, when we look at delay, then we've got this measure that, holds true across a lot of things. Okay, so how do we get a standing queue? This is another review, and let's think about a TCP that has a 25 packet window, and it's going into a path with should be AN, not AND, an intrinsic pipe size of 20 packets. So let's look at this classic Van Jacobson picture, which is very nice, that we've got things going in and it comes back from the receiver with ACKs. So let's say there's this initial burst of packets that fills up the queue. That's fine, that's good queue. And then we see it coming out onto the link that with time, this is like the size of our queue, it would be going down, right? But then we would say, well, but we've got these 5 packets that are just always there. You know, it might kind of go up and down because, you know, you pull the packet out and you might have 4 and then you've got 5. So the question is, you know, why would we want to keep those 5 packets around? They're not doing anything except taking up space. If somebody else arrives, they've got to wait for those 5 packets. The packets aren't arriving at the receiver any faster. So, okay. So Coddle's approach to tracking bad queue, this is the way I tend to summarize it, is the good queue goes away in around a round trip time and the bad queue hangs around. So if we use the observed sojourn delay, and this instead that's the time that's actually experienced by the packets that have been sitting in the queue, then what we want to do is see the minimum amount of delay that the packets experienced during an interval. And that will tell us the bad queue, because that says, oh, that hung around for an RTT or more. And this is only true if that window is at least an RTT wide. And so we want to be generous in picking that. And I just wanted to quote what we said about interval back then, which is that the interval is loosely related to the RTT since it's chosen to give the endpoints time to react, but we don't want it to be so long that, you know, response time suffers. But, you know, this is hard because round trip times are different everywhere. But, you know, what we've generally found out is it's better to be generous in picking that time. And so that default interval that we picked way back then when we were looking at just internet traffic was 100 milliseconds. And this was kind of chosen for, you know, US wide or possibly, you know, European wide internet traffic and not data center. But, you know, now having CDNs means that a lot of our intrinsic round trip times are a lot of times under 20 milliseconds. So one question is, should we change the default? And, you know, keep in mind that a too short interval can really be a disaster. But although if you've got a small number of long round trip times, you know, that are mixed with those other ones, they should kind of be okay because the drops get moved around and the chances of you hitting that really long flow, you know, the one that's longer than 100 milliseconds with every drop are probably low. But it's true that if you have the interval too long, it's going to take longer for the dropping to ramp up. So now what about if we want to target that sojourn time, you know, how low should we make it? You know, I said that, well, you know, we really want the queue to go away, but that is kind of a simplistic view, because if we are always trying to force ourselves to have a 0 sojourn time, we can, you know, really have issues with utilization. So what we really want to do is make sure that we, you know, leave a little bit of space there, that we force that during that interval, we don't want to force it all the way to 0. We want to kind of maximize our utilization, but minimize our delay. And also we shouldn't drop a packet if there's nothing behind it. That's the kind of thing that the old red AQM did, and that was an issue. Okay, so again, network power, which was also mentioned in Neil's talk, that's a measure of throughput divided by delay. And if you apply it to a single flow, that kind of gave us a ballpark of what we should be looking at for our target values. And this this particular picture, if you want to know more about this, you can go look off of my website. The really good thing to do is listen to Van's IETF talk from the time. And this suggested that we should explore target values in the range from 1 to 15 millisecond. And so when I did a lot of experimental work, and all I really had at the time was simulation, but I tried to, make different traffic mixes. It seemed like 5 milliseconds was pretty robust, and that also fit with a nice point on our graph. So we have gone with 5 milliseconds, and we had gotten a lot of early experimental evidence that seemed to be correct. I think, of course, this could be adapted for different circumstances. Our point about saying that, this is something you don't have to adapt was the idea that you could put it out there anywhere in the internet with these particular numbers and things should work pretty well. And and that seems to have been mostly correct, but now there's more than a decade's worth of experience that people probably know more than I know. So the other thing is, how often should we drop? And again, we're back to this notion of we don't know. Here I am, I'm sitting at my particular buffer in the internet. I don't know how many flows. I don't know what type they are. I don't know what their RTT is. So I want to kind of carefully drop things because my whole point was I didn't want to do any harm. I had looked a lot at how red worked, and I saw that it basically dropped the hell out of things in order to control them. And, for long-lived TCPs, they can often kind of recover. That's not so bad, but it also can play havoc with other mixes. So anyway, when a persistent queue is detected, which means that we've seen that we were over that target, we never went below the target during the last interval. Then what we'll do is we're going to go ahead and say, well, we're going to set our next drop time. Well, we enter a dropping state, and we're going to set our next drop time for the interval plus the target. So there's enough time for reaction. And after that, we decrease our drop time by the square root of the number of drops since the drop state was entered. So I want to kind of show a picture of what that looks like because I like pictures. So let's consider a apparently unresponsive traffic mix. I say apparently because this also could be something with a very long RTT. And the measured sojourn times have been greater than or equal to the target for an interval. And then this graph shows you how the start of the drop state and the subsequent drops. So let's say here it is. Let's say that it's been above 5, our target, for more than an interval. So here we see a packet and we go ahead and we drop it. And it keeps going up. This is a burst. And then our sojourn time kind of drops down and we just get this sort of pattern that you get, sort of a, sometimes when the queue just is slightly alternating a little bit. But since it's staying above 5 milliseconds, we compute the next drop to happen here. This is says, okay, we've already dropped once. So here's when we're going to drop. And now we go do the next one here. If you look at my little table there, it's 74 milliseconds, and 61, then 53. And suppose we're kind of going along and then all of a sudden, oh, look, we got one that was below. We pulled a packet out and the sojourn time in my queue went below 5 milliseconds. I exit the dropping state. So here's another picture where I want to say, look at what happens if we have an actual intrinsic RTT. By intrinsic, I mean without any added delay along the path. We have an actual intrinsic round trip time of 20 milliseconds, with an initial window of 10 packets in a burst. And after that, we increase the window by a packet every round trip time. So here we have these usual settings, and I just picked packet time on a bottleneck of 1 millisecond because that's easy. So here's the burst, and the burst, we say, oh, look at that. We got something with a sojourn time of 5 milliseconds. So we say, we're going to keep an eye on this. And that's why I used yellow. We went into the yellow zone. But, oh, we got a sojourn time that was less than our target, 16 milliseconds after we kind of went into the yellow zone. So we don't care. We're not concerned anymore. And after that, you know, it's like slowly building up. So nobody spends any time in the queue because there's no queue. Now we suddenly get here where we've got more packets going through the link than we are pulling out. So we keep building up, and we're doing this every one of the sender's round trip times. And then again, here we are, oops, we're getting greater than 5, or we're at 5. So we sort of stay in this, you know, what I call it a yellow zone. And look, we've been in there for our interval, so +5, so we drop. And we go ahead and compute the next drop, but in the meantime, we'll say if it's a Reno cubic type sender, it responds and it halves the window, and we're back down here again. So this, because it's a shorter round trip time flow, it means that we've under controlled in the sense that we're carrying some queue here, right? That's greater than our target. If we had a longer round trip time, like that's could have been the case on the previous slide, then it might receive multiple drops before it can respond. But in reality, we've got a mix of both flows, and you know, it's kind of who knows which one is going to get the next drop. And we hope that helps us out a little bit. Okay, so here's some really cool things about using sojourn time as a delay metric. And I should say the reason for this picture is, and the reason that I use sojourn time is because Jim Geddes kept bugging us from the start and saying, I need something that works when the Wi-Fi bandwidth goes all over the place. So that's what this picture is about. And I set up a simulation where the bandwidth kept changing kind of dramatically. And this picture's in the CACM paper. And what you can see here is that the tail drop, which has a bunch of delay, while meanwhile red and caudal are down here, is always kind of, you know, taking up everything. And this cool thing is here when we drop suddenly by an order of magnitude, the caudal starts to respond here and kind of drops down. And here's the red, it's looking at Q length. So it starts dropping faster, but we'll look down below to see what happens here. But then when we go back up, we've got all this delay. So the black line is caudal, which is pretty cool. It's just every time things change, it takes a while to adapt. But if we look down below, let's look at this upper line, and we look at the number of kilobytes that were transferred versus the simulation time. Caudal is staying really close to tail drop. And these places where it changes is just because of these, you know, changes we see up here, and it has to catch up again. And if we have undersized buffers like 10 packet buffers, they stay right together. But look at red, it wasn't doing throughput very good. So, and what was really cool about this, I thought it was cool, is that these Stanford students, they have a seminar where they tried to reproduce the things that people claimed in papers, and they experimentally duplicated this running on, I think, Linux machines. So I felt vindicated I do try not to lie in my results. Okay, so the other cool things about sojourn time as a delay metric are for a multiple queue length. And this was another place that was just, kind of crazy. People were trying to think about, well, how do we do AQM when we've got multiple links coming in? And if you're looking at queue lengths, you're all over the place. But if you look at time, sojourn time doesn't care how many queues there are, right? If we have one queue that has these 5 packets in versus 5 queues that each have a packet, and we, suppose we're doing this one, this one, this one, this one, same, right? Same results. So we might start knowing when we feel like things are getting a little full. So the other cool thing, which is FQCODL, is that you can use multiple queues to mitigate ACK compression and sort of unfair treatment of shorter flows, or just flows that won't respond can be in their own queue. And when you do that, then the smaller packets avoid waiting behind the larger packets, and then you can separate the flows for fairness. And you also solve the ACK compression problem you would have if the ACKs and the flows are mixed together and you've got, both directions going. So this is why we control delay, because it's the thing we want to control. We don't really care about queue lengths. So I just want to show this because this was kind of, I was taking these measurements, and I believe I showed some of this stuff the last talk I gave here. These are from some work that I did that I stopped doing in like 2017, so it's more recent. This is measuring the downstream delay on Netflix videos. And what happened here on this upper one is I measured it on my home network in March of 2016, and there was a round trip delay of 14.5 milliseconds, and that was measured with passive ping. And then there's these interleaved 3.2 megabit per second streams, and you see these huge spikes, right? They're going up over 400 milliseconds. And these are the median delays, these black dots. And you look at this and you say, oh, a delay aware transport like BBR would be nice. And that said, I'm building up a lot of queue, but my round trip delay is only 14.5 milliseconds. But failing that, if you had CODL in the path, you could fix it. But the interesting thing here is I tried measuring this again in September, and Comcast had nicely raised up our bandwidth to 180 megabits per second. So, we still got bursts, right? Because that's the way things roll. But now our bursts are, topping out, up here at the 20 to 25 millisecond range. And, but we get a much lower median delay per packet. So, this is probably more reasonable, but, maybe we don't really need the bursts this large either. But, I'm not going to go into the details of, I have other talks, and they're out on my website that go into the detailed behavior here. And I was really surprised. I guess Netflix still uses Reno. So yeah, it probably still looks like this. Okay, so here's the warning label on my talk, that the actual details of CODL and FQCODL as deployed have certainly evolved over time, and new transports should never activate the CODL drop state. What do I mean by that? New transports should do things where, I guess what Stuart called being rate adaptive, or, as Neil explained about BBR, right? They're trying to operate at that perfect point of of having maximum power. So this talk, really was about the original approach, and I was trying to explain, why we did this, and why we should should focus on controlling delay and not all these other weird metrics. And I think people know that more now, but you know, at that point, it was less of a known thing. Okay, I'm done.
Thank you very much, Kathy. That's very interesting stuff. We do have a couple questions. First, Frank is asking, what's your take on L4S?
Oh, I don't know very much about it other than that it's a thing that requires more cooperation from more parts of the network. And my focus has always been, even the work I'm doing now that has nothing to do with delay is, you know, here I am sitting at a particular point. What can I do? What can I control? And so that's what CODL is about. You know, what can I do? And I'm sitting here at my buffer so that I'm not part of the problem. And that's I believe that's kind of what BBR is about. I'm the sender. What can I do? So I guess if you have control over more parts of your network, you can do more things. But I don't know too much about L4. I don't do, I'm not working in this area, but nobody wants to talk about the stuff I'm working on now. So I have to talk about the past. So.
Well, we're certainly happy you wanted to spend some time talking about the past today. Thank you very much.
Thank you. Let me stop sharing my screen.
So our next speaker, and Gino from Nokia has actually said that he will not be able to join us today. So this will be our final speaker of the day, and that is Robert McMahon, or Bob, from Broadcom. He is an automation test and measurement engineer at Broadcom, and has a lot of expertise in packet forwarding and Wi-Fi, and has been the primary maintainer of iPerf2 since about 2014. So Bob, please.
Thanks, Bjorn. Hopefully you can hear me and see the slides.
I can hear you, but I cannot see the slides.
Okay, I got to do the start share again. Okay, now you should be able to see the slides.
Yes, now I can see the slides. Thank you.
Okay, so my name is Bob McMahon. I'm the iPerf2 maintainer since about 2014. And I also work with Broadcom, mostly in the Wi-Fi division. Get this up a little bit. Quick, Broadcom supplies chips for every aspect of networking in the data center, whatnot. And iPerf2 is an end-to-end tool, so I'll probably be not just latency related. I'm looking at how the testing of networks in general. Building networks is very challenging for people building networks, and then there's a tool set that that people use, and iPerf2 is one of the tools. So why does Broadcom support an open source tool? Primarily because we want a common yardstick, and we just provide it to the world at no cost in the hopes that we can all, it'll help people spend more money on improving networks versus buying test equipment. And it's maintained as open source to be transparent, so anybody can look at the code. It's chosen by users per its merits. There's really no word of mouth. I mean, it's all word of mouth. There's no marketing behind it. There's, and the other thing that if you use iPerf2, you'll get free statistical process scrolls across releases. Means that we test our tools so that they don't have statistical signals ahead of our chips, because we don't want the tooling to start causing statistical signals in our test environments. You get that free. This is sort of what's happening in growth. I think the main thing to note is that this tool is a network IO tool that uses Berkeley sockets. And it's end-to-end, so this is a quick picture of that. The iPerf is acting as an application and using the transport layer and TCP as a transport layer. So that's the view. So we're really trying to get a view of what does the application experience, and iPerf gives, as a socket application, it gives that perspective. So what have we done besides capacity? We've done a lot on latencies, rate controls, different traffic profiles, different pacing. We do support full histograms and multiple measurements, not just central limit theorem averaging. We added one-way delays, tail latency, You can keep going. Messages, TCP first write to final read. The responses per second, jitter, three-way handshake times. So one of the on the buffer bloat one, the EDEQ depth via little slog, that you can use that quickly to just get a rating on your device, because if you if you get to the little slog allows you to move between sort of space, memory, space, domain, and time domain. I'm not going to review little slog, but it's queuing theory stuff. And we also, with the outputs, the primary use for us is statistical process controls into machines and not so much humans, because we've got lots of rigs and lots of setups, and we need to have computers do the work for us. Some examples of things, everybody knows about buffer bloat and what it is. And so, but from my perspective at least, it's actually a memory size more than a delay. Understand that delay is the user impact, but it's really about how much memory is there. And like I said, using little slot, you can get the actual number of packets that are in the queue, and from an end-to-end perspective. I love this one, and this is a reminder that, from a coder's perspective, you really want to size your queues properly. You don't want them to be too big or too small. And then another thing, because a lot of people in the networking world think of packets, but from my perspective, or from an application's perspective, we're actually sitting on top of them. All these state machines, which are TCP/IP state machines, and packets are driving those state machines. So how packets behave is just one aspect. It's actually how do the TCP state machines, and this is, if you looked at a stack coder like Neil would probably tell you, this is a very naive state machine too. So, but this is, and there's lots of these going on any device. So that's what's sort of I kind of think of it like protein folding. That's the thing that's moving that you need to figure out, okay, why is my application not working well? There's a transport under there that's doing this stuff, and the packets are just an input to that transport state machine. And it's end-to-end on each end. A quick picture, here's some 20 flows. iPerf2 is multi-threaded, so you can add multiple threads with the P command. And here's some pictures where you can see that going to the tail latency, it's not just the tail latency of one distribution, it might be the tail latency, it's not just the tail latency of a single flow. You might have multiple flows in a Chrome load, and it's the worst case distribution that's driving your performance or your quality experience. So you have to really look at multiple distributions, and you got to look at the tail of the worst of the multiple. Another thing we support is different traffic profiles. Isochronous is just one. That's where every period there's a burst of packets, and sort of like if you had a surveillance camera, it's going to burst on some cycle. So you can have both a variable rate in the burst, but a periodic. Server-side outputs we support. A lot of people turn on iPerf and don't look at the server-side, but with our use cases, we do use server-side outputs. And this shows you just a quick sample of the CLT min-max variance versus a full histogram. So we do full histograms as well as CLT averaging. The human way to look at a histogram is through a PDF or a CDF. And then you can sort of say, what's my 90% profile? So that's this picture. And you can see that this histogram can't really be described parametrically, because there's no 2 numbers or 5 numbers that define this. So you have to really look at the full histogram. And that introduces challenges for us when you're doing lots and lots of tests. You might have 100,000 histograms to look at, and how do you do that in machines? So we use something called Kolmogorov-Smirnov 2-sample test. And it's basically, when you integrate the PDF, you get the CDF, and the max distance between the CDFs gives you a distance. And that distance, is roughly here. And that allows the tool to actually cluster your histogram, so we can look at clusters as opposed to individuals. One thing people don't really know about that we support is Python interface. It's in the same code base. I'll go through that. One hope is people will start to introduce common tests in Python, and we could release that as part of the tool as well. History, don't really care, but iPerf2 basically 2 is less than 3. So if you're trying to do low latency, use 2. If you have multicast, use 2. And if you need threads, use 2. And if you need statistical verifications across releases. Used to. Features, don't care too much. Okay, don't care. That's basically it. I wanted to show you a few more things just for in case you're interested. One of the key things with iPerf2 is one-way delay metrics, and to do that, you have to figure out clock sync. And today, with Raspberry Pis, you can build your own highly accurate Unix workstation with a GPS chip for less than $150. You can, and this site will give you how to do that, and you can pull out your soldering gun and get a nice for about $20 you can get a GPS discipline workstation. I mean the GPS chip in the antenna, and then the Raspberry Pi itself. So this site here goes through how to build an L4S system, including clock sync, which is kind of nice. So going to the clustering, how much time I got? I'll try to close it up quick. So here's an example. This is only a simple 10 unit cluster, and I don't know if you guys are used to dendrograms, but this tells you can sort of see by these dendrograms that there's 2 clusters here of interest and how it's just produced using the Kolmogorov-Smirnov. So I know if I look at that, like 357 looks similar and then 2904 looks similar. So let's go see if that's for real. So you go into, I think it was 2 I was looking at, right? Yeah, 2. So 357, let's go to 357. So it says 3, 5, and 7. So let's look at 3 and 5. Yeah, pretty close. Let's look at 2 and 2, 2, 3. Now you can see that was one of the max differences, and you can see that, yeah, those histograms are very different. Let's look at 2 and 9. And these ones landed the same. So the nice thing about Kolmogorov-Smirnovs is that it's non-parametric, and it can be any histogram, and you can do the clustering around it. And so this really helps from a perspective of if you have lots and lots of histograms, how do you actually do any kind of analysis against them? And having this ability to cluster and measure a distance between them is a big deal. I think that's pretty much all I cared about, except for maybe this. If you want this kind of capability, it seems complicated, but it's actually not. You instantiate a flow in Python, you run it, and then you compute. And so it's pretty simple. And this is all released in the code, so you can get this kind of analysis built in for free. And I'll stop there.
All right. Thank you very much, Bob.
Yep.
I don't see any questions right now. So if people do have questions, add them in the chat or use the Q&A tool for that. And thanks again, Bob.
Yeah, thanks for having me.
So that is that concludes our list of presentations for today. And before we sign off, I would like to sort of say a few words, a short summary of what we've been seeing these last 3 days. We've heard from open source developers, big tech, big telcos, and big telco vendors, CDNs, network hardware companies, network software companies. We've heard from application developers and from researchers. And all in all, I think it's a fairly comprehensive cross-section of our entire industry. And the fact that it's even possible to bring such a diverse group of people together for a single topic just goes to show that we're all onto something important here. And that there are a lot of things happening all at once in this field at the moment. So I hope we can do this again sometime next year, and I hope that by that point we will have even more progress to show. So finally, if you're going to take away only one single thing from this event, I've made it super easy for you with this very simple diagram. So as you can see, stable and low latency is what we're really after here. And with that, thanks to everyone for attending, and thanks again to all of our speakers for sharing their knowledge. I hope to see you all next time. Thank you.